What would you need to store if you wanted to reverse time a la Braid? Well, that's kind of an open-ended question, so it's hard to say, but it does relate to physics very directly, and so I'll point this out. So the rigid body dynamics simplification, remember I said we were doing rigid body dynamics, which is a simplification of physics that basically says, all right, I've got some collection of atoms, right, that makes up, this block that I want to simulate. And I'm going to simulate it by reducing it down to its center of mass, which is some position inside it, and its orientation, right? I'm just going to say that that's what I've got. And I'm going to simulate just that center of mass and that orientation, and I'm going to assume that all the atoms in the block just obey that and get moved along with it, right? That's the simplification. In that simplification, a lot of things just aren't real. They don't work the way that they normally do in terms of the microscopic level because we're making a bunch of simplifications. And the eye can't see these differences, right? The reason rigid body dynamics is so useful is because it captures basically all of the interesting things that happen when non-deformable objects do stuff. Now, there's deformable body dynamics, which allow things to squish and do other sorts of things, and that's a separate thing as well. It's another simplification, but ignoring that for a second. So the reason that we use it is because those equations of motion capture all of the things that our eye is used to picking up on, and we go, oh, okay, good, right? But one of the consequences of it is that it's non-reversible, right? So you cannot, for example, take the state of the world, flip all of the quantities, and run it backwards and get back to where it was 15 minutes ago. And that's not because of our piecewise approximation, right? Our piecewise approximation is another thing that I'll get to in a second. But I'm actually talking about the actual non-participatory, if the user wasn't even controlling someone, the actual non-participatory rigid body dynamics are simply non-reversible. And the reason for that is friction. So basically what happens is when something slides along the ground or when it hits air resistance, whatever, energy is lost from the system and things slow down. Now in the real world, that's not true. There's all sorts of stuff that happens in physics, and I don't pretend to know all of this stuff, but like, you don't really have stuff just slow down. It produces byproducts like heat that are, transferring atoms, like all of the quantum physics is happening. There's all this stuff that's happening. So to say that it was non-reversible is a very different statement, and I think it may actually be reversible. I don't even know. I don't know where physicists are on that kind of stuff. They come up with new theories, who knows? But what we do know is our simplification is very non-reversible because basically what happens is the state of the world, let's say this was a die. Let's say this block was a die, a die that you play, craps with or whatever. You roll this die, it comes to rest on the table. That's the end of the entire information you have. So when that die, it bounces, it comes down here, it bounces, rolls, and lands here. If I wanted to get back that motion, if I wanted to reverse time to when the die was in the guy's hand before he rolled the die, well, I've got no information to do that. His velocity right now is 0. I can't negate it and have him move back to where he was. And so that non-reversibility means that in order to do like braid-style rewind, like you were asking, you actually have to store the state of the world at least at key junction points, like when things stop and when they're not in free-form ballistic phase motion, where you know that you can just play it forwards and backwards and it'll be the same. So anytime there is friction, you have that problem because energy is being lost from the system and not accounted for anywhere else, right? Another way to do it would be to record the friction forwards and then play it back, whatever. The way Braid actually does it, I think, is just with compressed records per frame. Like, I think he actually just compresses like a rewind stream and plays that backwards, I believe. I don't remember how John ended up deciding to do that. But we would probably have to do similarly. Like, we'd probably have to do something where we stored records of guys' paths because these things are non-reversible. You can't just play them backwards from state to state. You have to actually know what happened to the guy in the past because the system is lossy. Let's see. Is the character a bitmap? Yes, the character is. We showed asset loading like last week ago, I believe, and we loaded him in. He's actually 3 bitmaps. You'll see, hopefully, maybe by the end of the week, but if not by the end of next week, he'll also be kind of bouncy because he's made in separate pieces, and so he can kind of bounce and stuff. So we'll be doing some more with that. Let's see. Let's see. When would you want to use other integration methods? I've read Euler is great for everything. So actually, isn't this already Euler? This is forward Euler. Are you thinking of backwards Euler? All right, so those are numerical integration techniques. So we can start with that. And also, this is actually not really integrating in any particular way like the sort of stuff that you're probably thinking of, where you have to take large solutions of things. Let's table that for some other time, because that's like that kind of question is probably best left for when we have something a little more complicated that we might actually want to consider something like backwards Euler for, which I don't know if we're ever going to get to. But basically, like, stable numerical integration is not necessary for what we're doing right here, because we're never going to get into a situation where this wouldn't be stable. And so thinking about things like the choice of integrator is not particularly important. And so I just don't know if that's ever going to be within the scope of what we're doing. But yeah, it's a good question. Oh, and then I hit return and find out that he wanted to correct that question to, I've read Euler isn't great for everything. That makes more sense. I was like, why are you saying that we're not doing Euler? I'm like, we're doing a forwards Euler. Maybe you're thinking of backwards Euler. I don't know. Okay, so let me address that slightly then, because I can answer your question a little bit better if that's what you're thinking about. So the reason that sometimes you have problems with integration systems is because they can get out of control very quickly. So the problem is, if you think about what happens here, there is a time step, right? And that time step, like I said, we're pretending starts at f0, we're running it to f delta t. And we're basically saying we have some function that says where our guy is going to be over that time step. Now, what can happen is you can have certain equations of motion. This is probably not going to be one of them because of how simple we've set up things to be. But if you had a complex system of stuff that was pushing on each other or doing whatever it was going to do, you can get into situations where the function that you're trying to represent has some very critically bad behavior when you try to integrate it. And typically when you're looking at things like this, you're talking about doing integration that's not analytic integration like this. This is actually fairly analytical integration. We've actually created the full equation for position. We've just created it piecewise, and we're just flat out solving it, right? But what happens a lot of other times is you're actually doing these equations of motion as approximations to things that are actually a lot more complicated. So instead of, like, this is the actual equation of motion for the guy. This is actually what it should be, and we're just actually solving it. But if instead what we were going to do is basically point sample some set of information for this acceleration, right? Where instead of saying, well, we're just assuming that the guy holds down whatever key he holds down and the guy moves in that direction or whatever, right? Let's say that we had some really complex physics function here that was going to produce the acceleration right here. And then we're going to assume that over this time step that acceleration is constant, and we're going to solve up to see what the equations are. Well, that could be very dangerous if these equations are very stiff. And what that means, the stiffness part of it means if they have some very sharp, how should I explain this? This is really an explanation that's way ahead of where we are. So I'm trying to think of how to explain this in some kind of nice way. All right. Supposing, here we go. Supposing I was to tell you that I wanted to integrate this like function here, right? And I wanted to be able to basically say, all right, what we're going to do is we've got frame time steps, right? And I want to basically say, I want to trace out this path, but I'm only going to actually be able to sample at certain points in the path, right? And what you have to remember is the state of the world, right? The state of, if these equations of motion get more complicated, then we don't actually know what they actually look like in practice. That's when you have to go up to more fancy maths. Like I said, I'm kind of dancing around this here, but what you have to imagine is that you're actually in a field of functions, right? That basically, like, there's a family of functions and you don't know actually where the one is that you're trying to follow, okay? And so at any point in this field space, I can basically say, all right, wherever I am, tell me what the derivative of this function is. I'm going to step the equations of motion forward to the next time step, and that's where I'm going to say everyone is. And then I'm going to look again, and I'm going to look at the derivative, and I'm going to do the same thing, right? Well, what ends up happening if you have these sorts of situations where the equations are complicated enough that you can't write those simple closed form, things like what I just did, is you can see that you get into problems very quickly, because what's the derivative here? Well, the derivative points up in that direction. I step that far and I get to my next time step and I say, okay, I'm here, what's the derivative? Well, the derivative is this really steep thing that goes up there. I come here and I go out to here and I go, oh, all right, bad news, guys. We're nowhere near the old function. But I don't know that because I don't know what the function actually is. I just know it's this very complex thing that can't be analytically integrated. So now I'm here, I take the sample of what the derivative is there, and the derivative is pointing back down here, right? So basically I step down here and I get here, and maybe this thing curves up again or whatever, and so I step out there. And what can happen if you're in a very bad situation, where these lines kind of all go up like that, like let's say that they look kind of more like this sort of a thing, you could get into a situation where you just fly off into space and you're nowhere near the old thing that you were if you're doing forwards Euler, which is the name for the kind of integration that you do where you just sample the derivative and step forward, right? One solution to this is backwards Euler. And this is why I said, when you said I've read Euler isn't great for everything, it's forwards Euler that isn't great for everything. It's forward Euler that's not great for games. Backward Euler is actually very good. And what backwards Euler is when you go to the time step that you would next be on. So instead of doing it this way, where we took the derivative and stepped forwards, instead what you do is you go to the next time step and you search along this line, essentially, for where points back to the place that you were at. So it solves it in reverse. What that means is you can never have something out here because this guy pointed in a totally different direction, right? So what would happen when we took this time step is we'd come here and we'd look for some point in this area that pointed back to where this was, right? So it would be somewhere that was kind of like down here, right? It would be off the curve, but it would be off the curve in a less energetic place. Right? So it sucks the energy out of the system and brings things back to rest when it is wrong, rather than flying them off into the middle of nowhere when it is wrong, right? And so backwards Euler is actually very good, but it's much more expensive, which is why you often don't do it. So I don't really want you to think about what we're doing as forward Euler, though, because all this stuff is stuff that is way outside the scope of what we're doing. This is numerical integration. And we're not really doing numerical integration. We're basically doing analytical integration. We're just doing piecewise analytical, which I realize sounds like hand waving because piecewise analytical, why isn't that numerical? Well, it's because I'm actually saying these are actually the equations of motion for the guy. And we just happen to change what the constants are when the user pushes the button, right? But we know what they are and we can integrate them up analytically. I just did it for you. We showed the 1/2 AT squared thing. And so we're not really doing something that falls into this category. So hopefully that answers the question there. And we're kind of way over time here, but let me just take a look and see if there's anything else. Vector math is very important because it's in sort of the same way that you could think of C and C++ as getting you a level above assembly language so that you can start to think about things at a slightly higher level while still retaining most of the performance benefits and the sort of direct access that you're used to. Vector math is kind of like that for the scalar math that we've been doing. It basically allows us to do the same sort of operations we were doing when we were manhandling the x and y coordinates of things and this sort of stuff. But it gives us the opportunity to start thinking about those as a pair and start defining operations that work on them as a pair, which we can still use to get very efficient code, but it allows us to sort of be up at a slightly more higher semantic level. And sometimes you still have to go down there and muck with the individual values in these vectors, but most of the time you can start thinking of them conceptually, and it allows you to do a lot more powerful stuff. Now, we already did some of that. We already did some of that yesterday, in fact. But before I dive into that, let me quickly go over, as I always do, how you can be coding along at home. If you are someone who has pre-ordered the game at handmadehero.org, you should day 40 about what we had just done in the game, and then let's talk a little bit about what we are going to do today to kind of continue along in our vector sorts of experiments here. Okay, so we had just finished implementing simple equations of motion for our little guy here. And basically what we've done so far is we had made a little tile map, right, that the guy could walk around on. We had this, we don't really have, there's just sort of a static background sitting in here now. So we haven't gotten to how we're going to render our tile map yet, but we do have the ability to kind of draw these, the sort of white walls and the doors and stuff. So he can go up a virtual staircase, he can go out the side of the screen and so on. And we just implemented the equations of motion for him. So basically he has, sort of more of what you would expect a object's movement to be when you are moving him around, right? And so as I'm moving him around, I can kind of feel that momentum that we added, and he stops. He has a little bit of sort of a glide to a stop, and he has a little bit of acceleration when he picks up. And that just makes all the difference in terms of feeling good about the character motion when you're moving around. He's already much more engaging to move around than he was, even with just that simple change. And so that's sort of what we need to be focusing on, what we need to be doing for our player movement code, certainly. But we're also trying to learn about vectors here. So what I want to do is perhaps talk a little bit more about some stuff that we can do with the vector code to sort of see how it works at a little bit, starting to think about it in terms of slightly higher level stuff. Okay, so one of the things that we did in terms of using the vector math may actually have not been all that obvious, and I sort of mentioned at the end of last stream, but I want to mention it again because it's very important, is you'll notice that when I did all that talking about the equations of motion yesterday, and I sort of was talking about how, a little bit of a fat finger typist there, when I was talking about how we were going to do the equations of motion, and then we typed them in, and we did the equations of motion just like I derived them, and they worked the first time. We just typed them in, and they worked perfectly. It was great. And then we tuned the constants to make the motion be what we wanted it to be in terms of how fast he accelerates and how much drag he has, that sort of stuff. Well, what turns out to be the case is all of that derivation that I actually did, I just kind of did it as if it was scalar, right? When we did the integrals and stuff, and we did the work on the equations of motion, never did I actually ever say that we were working in vectors at all. We were basically just working with scalars. And so when we typed in this equation, we essentially just typed in a scalar equation, right? All we did was just solve, we basically worked out some scalar equations in Krita, right, when we were drawing them out. And then we typed them into something that is essentially a 2D process, right? This guy can go in, in any direction he wants in this 2D plane here, right? He's totally smoothly moving in 2D. And we didn't have to really account for that at all, right? We totally just were able to work with those equations just like they were scalar equations. And then we plugged them into something that was using vectors, and they just worked. And that's kind of, again, just a little bit of a slight hint about why you should always care about things like, sort of these more powerful math objects. Is just because they allow us to do things like that where we can simplify thinking about stuff. Instead of having to think about the x's and the y's and the z's and whatever, we can just think about sort of abstract quantities and know that they will apply. Now, there's sometimes that we have to think about things and know that they're actually vectors. And so there's things we have to learn in the math that actually depend on the fact that things are vectors. But for a lot of the time, you can actually think about scalar and vector interchangeably, and that's very powerful. So there you go. So what I thought we might do today, and someone actually mentioned this on the stream, so that was kind of fun, is I was thinking that it might be useful to a good thing to learn about vectors would be to sort of see how we would do a bounce, how we would do a bounce off the wall, for example. So when this guy comes down here, if he were to bounce, and his velocity would be reflected, in the other direction, right? And so what I was thinking about is maybe we'll just construct. There's a couple of things we could do, but I was thinking maybe we'll just construct that case. We'll just say when our hero here hits the wall, we want him to bounce off of it as if he were, sort of a bouncing ball. That was one thing I was thinking we could do. And then another thing that I would like to do maybe is make an actual jump for him, where even though I don't anticipate this character jumping on command, he is going to have to hop. And so coding in a jump is going to be interesting as well, because that kind of involves this concept of height off of the ground, which is something I also want to get into. So we have a couple of things we can do, and I think maybe the bouncing would be an interesting one of those, because it allows us to talk about some of the vector math. Now, we probably won't actually want the character to bounce off the walls in the future, because that doesn't make a whole lot of sense for him to do, but we will want things to bounce off walls almost certainly, and so we need to learn how to do this code one way or the other. All right, so if I go over here and start to construct the case so we can start to talk about that, let's think about what we have, right? So let's say I've got a wall here, right? There's my wall. And I want to start to think about what's going to happen when this fellow bounces off of it, right? And so I'm going to imagine, just for sake of simplicity here, I'm going to say that the bounce point is at the origin of the world, right? This is at 0, 0, right? It doesn't really matter because that's a free translation. I could move everything in the world such that that were true for the purposes of doing this computation, right? And then move it back afterwards. So translation, I can always translate things to a convenient location if I want to. So I'm just going to simplify things by saying that that's what's going to happen. And so what I want to do is I want to say that there's going to be some kind of inbound vector here, right? There's going to be an inbound vector. And what we want to do is we want to take this inbound vector and we want to reflect it. Well, it's hard to draw today for some reason. I can't seem to draw good lines today. We want to reflect it out the other way, right? The sort of the notion of what's going to happen when you do a bounce is something coming in is going to get reflected almost as if this thing was a mirror, right? And so we want to think about the incoming vector as somehow giving us the information that we would need to compute whatever the outbound vector is, right? And so what exactly is happening here in terms of this impact and response, right? Well, there's some things that we probably aren't going to think about really. Like I said, we're not doing deformable dynamics, so like the fact that when something hits something else that makes a dent or things like that, we're not really going to think about at this point. But what we are going to think about is the fact that whatever is sort of the velocity that comes in here, in some sense that velocity has to be conserved, right? There's a certain amount of physics involved here where if we've got a certain amount of velocity coming in, we'd expect that amount of velocity to be the same leaving, right? Because of conservation of momentum and so on, all of your nice physics laws, minus however much energy goes into this impact. Right? So there's probably going to be some amount of energy lost in the fact that you do make a dent and so on. And so we may want to simulate that as well, that loss of energy that comes in here, in addition to what's going to happen otherwise. Even if we don't simulate modifying the wall, we may want to make the bounce more realistic by saying that it doesn't bounce off at full speed. It loses some of its energy in that impact, right? Now, what's happening when this thing hits this wall, right? Well, one of the interesting things about this is this case starts to talk about vectors in terms of their components, and it's kind of interesting to sort of see what's going on there. Well, what's going to happen is, if I look at, I know that this vector is composed of two pieces, right? Because we've talked about this quite a bit. It's composed of its y portion, and it's composed of its x portion, right? And if I think about what happens to this vector, well, the wall is only stopping one of those portions, right? It's only stopping the y portion, right? So if I wanted to reflect this guy, I really don't want to stop his x motion at all. His x motion can continue just as it was because there is no wall horizontally here to prevent him from going somewhere. It's only this wall here that's preventing him from moving vertically, right? And so I could think about taking this vector, this velocity vector, this is the speed at which he's coming in, right? And I could take that velocity vector and just think about flipping it, right? Because this is the vector, you know, if it was based up here, that's not really the vector, right? The vector's actual value is whatever these two components are. So if I think of the vectors being rooted at the origin, it actually looks like this, right? And so what I want to do is preserve this amount, right? So this outgoing vector here is going to have this amount right here, this x amount. It's going to have the same as the incoming. The outgoing velocity is going to have the same as the incoming, right? But its y component is going to actually just be the negative, right? You can kind of see that whatever we thought, however fast we were moving in that direction, we're going to flip it up to here, right? And again, we could, after we compute this vector, we could do various things to talk about like treating it as if some energy was absorbed in the impact. We could lessen the amount that it bounces this way. We could just lessen its speed in general if we want to go in the same direction, but lessen it. So we could think about various things to do here. And that is how we would do that bounce, right? But there's something interesting that I've baked in here. And this is the part where it starts to get, because, I mean, if you were to look at this, you'd say, oh, well, based on that description, Casey, it's pretty easy to understand what's going on. If this is the incoming velocity, so this is the old velocity, and I want to compute that new velocity, right? What would I do? Well, I just told you what to do, right? If v, right, is equal to vx, vy, right? It's got two components. It's got the x component of the velocity and the y component. I just said, well, the new one's going to have the same x, and it's just going to have a negative y. I pointed that out on the diagram. It's kind of obvious, right? There's not much to do. So why are we talking about this? And in fact, it doesn't even look like a vector operation. It just looks like we're operating on the scalars again. You know, and at this point, you're just like, I'm going to go watch John play Nuclear Throne on the other channel because, frankly, you're not teaching me about vectors at all. You're teaching me about scalars, and I already know about scalars. Fair enough, but there is a rub here. What I drew was the convenient diagram where the axis along which we were doing this reflection was aligned with one of the primary axes, right? X happens to be the wall, and that is why it is y that can simply be negated. What were to happen if we had the same situation, right? Even still at the origin, let's say, but now I have a slightly inclined wall, right? And so I'm actually talking about a wall with this normal to it, right? This is the sort of the surface pointing out of the surface of the wall, right? Whereas here, the y-axis was pointing out of the surface of the wall. And now I've got this incoming thing, right? Well, now if I were to take that incoming thing and put it here, right? And look at what I want to have happen in terms of that reflection about the wall, because this is the wall, right? This is no longer the wall, this is the wall. Well, what am I going to do? That's not the y component anymore, right? These things have drastically different y components. There's the y component of that one, there's the y component of this one. Ain't no negative going to fix that problem, right? You are not the man now, dog, if you think that you're going to do this, right, to solve this problem. And so this presents us with our first sort of point where we have to start thinking about vectors in terms of the actual structure of them, in terms of the actual fact that they are vectors and not just scalars, because now we have to start thinking about how do we work with vectors in ways that do not involve falling back to the scalars when we need to do something on just one part of them, in just one piece of them, right? And so the answer is simply that we need to get familiar with, remember, I don't know if you guys were with me the whole time, then you remember me talking about something called the Hadamard product, right? And I don't remember is it 2Ds? I don't even remember. Is it that way or is it that way? I don't actually know. But I talked about the Hadamard product and I said, well, that's what happens, if I have two vectors and I want to multiply them together. I don't really want to write cross, I'm going to write that. If I have two vectors and I want to do some kind of operation between them that's multiplication, well, one way to do it, right, is to multiply the components together like so, right? A times C, and that goes in the x component, right, and B times D goes in the y component. That's called the Hadamard product, and that results in another vector. Well, that's really, like I said, not that useful for a lot of the stuff that we want to do. So now it's time to get acquainted with something that is very useful for the things we want to do, and that is the inner product, or better known oftentimes in game development circles as the dot product, okay? That is what is going to allow us to solve these kinds of problems with relative ease. You'll notice I don't have almond milk today. I've got tea. I'm doing some Bengal Spice. That's basically what's happening right now. All right. So, excuse me. Let's take a look at the dot product. Try to remember these diagrams. I don't have room for everything. So let's take a look at the dot product. What I wanted to do, right, is I already showed you how to solve the problem if everything were axis aligned. And so what I really want to do is I want to kind of have the ability to make my own axis systems, right? Like if I could have just created a new axis system that happened to be aligned with the wall, then I could have used the same solution that I used before, right? But I don't know how to do that. And so what we're going to look at now is we're going to look at how to use the inner product to do those sorts of things. So what is the inner product? Okay, so if I have two vectors, right? Here's one vector, and then I'm going to do this magical thing, the dot product. I'm going to do the dot product here. If I have AB and I'm going to do the dot product of AB with some other vector, CD, right? Then what this actually does is instead of producing another vector, meaning instead of producing something like the Hadamard product where it had two elements and it was another vector just like the two that came in, this is actually going to produce a single value as a result. It's going to contract these two vectors down into a scalar. And the way that it is defined, right, is it is defined to be the members multiplied by each other and added, right? So it's A times C plus B times D, right? It is A times C, B times D. Now, this jumps ahead a little bit for me to explain really how this is working exactly, because we haven't quite gotten into matrix math yet. But one thing that is interesting to note, and I'll kind of show you how this works, is the way matrices are multiplied is actually very easy, and I alluded to it on an earlier stream, in fact. But if we were to think about these as matrices, and we were to think about this the first part of the dot product here, this fellow right here, as being turned from a column into a row. So if we were to think about it being aligned this way, right? And then we take this guy and we leave him as his columnar form. And we construct the multiplication of these two in matrix notation. Well, matrix multiplication is actually very simple. For each element that you want to compute in the result, it's basically just as easy as drawing a line to find out where in each vector you hit for the element. Now, of course, there's only one element in this result here. If there was two matrices here, we'd have more of them. But then you just work your way down, starting from the outside first, right? A and C. You multiply them together, and then you add. You go to the next one down, D and B, right? There we go. And that is the dot product, right? Now this works for vectors of any size. It doesn't matter how long they are, right? It doesn't matter at all. You still would know exactly how to produce them because as many as I have here, D, E, F, right? G, H, I, J, K, L. I just take the first ones, I multiply those together, GA. I take the second ones, right? BH, and I just multiply and add all the way till I get to the end, F and L, right? And that is how you can produce the product, right? Very easy. And so oftentimes, there's the operation of changing something from a row orientation to a column orientation like that is called a transpose. And so oftentimes you will actually see the dot product, and it's called the inner product as well, like I said, because of this exact look, how it looks like that. You're getting sort of the inner portion here, right? It's hard to say without the matrix because there's a thing called an outer product as well. If I were to flip these the other way, it would produce more values. In fact, let me just show you because it's kind of interesting. If I were to flip these the other way, C, D, A, B, right? I can produce the outer product. And again, I follow the same rules. Do that intersection, right? C times A. And that's it. There's nothing more to do in either that row or the column, right? So that's one entry in my resulting 2x2 matrix. Do it again here, D times A, right? There's another one, C times B, D times B, right? You can learn matrix math in no time because basically just learning that is all you really need to know and you can compute any matrix product that you want. But again, until we actually learn what any of these things do, not particularly useful. But I just want to show you that. This is an outer product, that's an inner product. And you can kind of see why it's called that because these two things like kind of form the smaller space there and the larger space here. But anyway, that's neither here nor there. All right, so the inner product, dot product, are oftentimes called the scalar product as well because it produces a single value, no matter how big the vectors are, is something that is of great utility. And it may not seem like a very useful thing right now because you're looking at that going, why would I ever care about that at all? But the truth is it's actually quite useful. And the reason that it's quite useful is because this value, despite its innocuous look, actually computes to something very handy based on what these vectors actually are. So let's take a look at what that actually is. And I won't probably go through the trouble of proving it all because math proofs are only interesting to some people sometimes. But point being, I'll show you the sort of the intuitive stuff and how to think about it. And if you want to know the proofs, I can actually, maybe we can talk about them on the forums or something like that. Anyway, so the dot product. If I have two vectors, so I'm going to go ahead and say that my vectors are now A equals AX, AY, right? And B equals BX and BY, right? These are my two vectors. And somewhere in space, right, I'm going to think about these guys. Here's my coordinate system, and I've got two vectors, okay? Like so. Now, when you compute the dot product, again, often written as this because of that transpose. The T means the transpose. Remember, I'm turning one on its side and then multiplying to get that thing. Oftentimes written like this, can also be written just as a dot and so on. There's lots of different ways to notate it. I tend to use that one, A transpose B, because that's just the same in matrix notation. So that's the dot product there, right? So that, which again is just going to be AX, BX plus AY, BY, that's the entirety of it, right? That's all it is. That quantity actually equals something rather useful. It turns out that it's equal to however long, and this is one way that length is often written, so I'm just going to write it that way for now, however long A is, right? And so I'm going to call this A and this B over here. However long A is, scalar-wise, right? Times however long B is, scalar-wise, right? So that length here. So this guy is that length, and this guy is that length there, right? Times the cosine of the angle between them. So these two guys here, they've got this angle here, you're right? Let's call that theta. The angle between the two vectors, whatever its cosine is, times the length of B times the length of A, that equals this quantity. Because remember, this is a scalar, because this is a scalar length. That's how long A is, this is how long B is, and this is how long, and this is the cosine of the angle between them, right? Well, again, if you want to prove this, you use the law of cosines. If you know geometry, I'm not going to do it right now, but basically you can prove this using the law of cosines. If you're interested in that, you can go check it out. But anyway, this quantity constructs that actual identity, right? It actually, this scalar value equals this scalar value. And with just that one relation, we can do some incredibly powerful stuff, actually. So what stuff can we do? Well, for starters, what if we wanted to know the length of a vector? Like, I want to know how long A is, right? Well, there's two ways we could think about doing that, right? One is that I told you about the Pythagorean theorem the other day, right? So we could take, here's AX, here's AY. We want to know this length here. We could do AX squared plus AY squared equals whatever the length of A is squared, right? And so that is how we would compute that length. We would root this. So we would go, okay, root AX squared plus AY squared equals length of A, right? That's what we would do. And that is one way to compute the length of A in terms of thinking about how it's done, right? Another way we could think about how it's done is just by using this equation. We have something in it with the length of A, right? So what if we were just to take, instead of doing A transpose A, and instead of taking A transpose B and taking the dot product with B, what if we just take the dot product of A with itself, right? Well, if I take A transpose A, just following this equation, I would get the length of A times the length of A again, times the cosine of the angle between it and itself. Now, we know that the angle between it and itself is 0, right? So what's the cosine of 0? Well, for those of you who don't remember your sines and cosines, all right, you know who you are out there. I'm going to draw the circle. You could always draw the circle if you get scared, right? You could always draw the circle. This is the starting point on the circle, right? We wind up to here, right? That's 90 degrees. We wind to here, that's 180. We wind to here, right? That's 270. Wind to here, and that's 360 again, right? This is 0. Similarly, if you're doing this in radians, if you guys remember your radians, it's 2 pi out here, right? So this is going to be pi over here, and this is pi over 2, right? And this is 3 pi over 2. Remember the circle. As we work around the circle, right, the cosine is the x-coordinate of the point on the circle, and the sine is the y-coordinate of the circle. So if I was at 0, which is right here, right? Well, there ain't no y-coordinate. There's just the x-coordinate, and the x-coordinate is all the way out, right? So the cosine of 0 equals 1, right? Cosine of 90 equals 0. Cosine of 180, negative 1, right? Comes back around, and so on. Hopefully you guys are all familiar with that. If you're not, get used to your unit circle. Unit circle is the man now, dog. Is good. Okay, unit circle, good. All right. So if I do this, and I know that this is 1, because there's no, the angle between A and A is always 0, right? It's right on top of itself. I know that falls out, and I just get length of A times length of A, which means ATA equals A squared, right? So the square root of the dot product of A with itself is the length of A. Not surprising, because guess what? This is the equation for the dot product, right? What would happen if these were A's? It'd be AX squared plus AY squared. Exactly what was inside my Pythagorean theorem. The Pythagorean theorem and the dot product are very intimately related, right? And you can see that. Okay. So, what else can I do with this? Surely I did not spend all that time teaching you how to do something that you already knew how to do and that we already did yesterday, and that's correct. I didn't. There's a lot more stuff in here that we can use. All right. What is it? Ooh. Whoops, didn't mean to quite get that overzealous. All right, there we go. All right, so what is it that we can do with that, right? What is it that we can do with A transpose A equals length of A, length of B, cosine theta? Well, the cosine theta is the part that really comes in particularly handy, right? The reason that that comes in particularly handy is because when we start to think about the cosine of the angle between those two vectors, right? If we start to think about what that actually means. Well, what if we could take one of these guys out of the equation, essentially? What if we could just say, a priori, let's take B, and let's say B is a unit vector, right? A unit vector is a vector with length 1, right? So if I said the length of B was 1, it's 1 unit long, then it would drop out of here, right? And if B is length 1, then we get A transpose B equals A cosine theta, right? That's what we're actually going to get. So what does that actually do for us? Why would I care about that? Well, the reason I would care about that is because imagine that now we have our wall again, right? That wall we were talking about. Suppose we had, right, a unit vector that was pointing the direction away from the wall, right? Just suppose that's something we had. Well, now, if I have some other vector, right? I've got this vector here that's, this guy's doing his incoming bounce, right? And so this is the vector. That's that incoming velocity. This is that incoming velocity. So here's my vector, B, right, in this case. And I guess in this case, I want to say that this is A for our equation, right? So that incoming velocity is A. Well, if you take a look at what actually happens to these two vectors, I know that the length of B is out of it. So the result is going to be however long A is, which is this length right here, right? But multiplied by the cosine of the angle between the two vectors, right? And that cosine, again, is going to be this right here, right? And to see this a little bit better, maybe it's kind of hard on the diagram. Let me do it with a more, in a perhaps a slightly more acute way. Let me bring it out here, right? So that we don't have to have it sort of be bent back. Let's suppose that they were more like this, so they're a little easier to see, right? So I know my result is going to have the length of A in it, but I also now the cosine of that's between these is now going to multiply it out. And what does the cosine of a triangle do for us, right? What does the cosine of a right triangle do for us? Now you should remember this again from your grade school trig, right? What does the cosine of a right triangle give us, right? Well, it gives us this. It gives us this edge right here. If this is the hypotenuse, right, then this is cosine theta h, and this is sine theta h, right? That's exactly what that gives us. It gives us the length of that side. And the sine gives us the length of the other side, right? Times the hypotenuse, however long it was. Again, this is stuff you should hopefully all remember from your grade school trig. Well, what did that construct up here? If I was to build that right triangle, right, that's built off of this angle, I'm getting this. I'm getting this amount right here, right? That's what I'd be getting. Because I know that I've taken the length of A into account, it's right here, and I know I've taken that cosine ratio into account right here, so this is just like here. Just like h cosine theta gives me the length of this side in that standard right triangle that you're used to, length of A cosine theta gives me however long this guy is projected effectively onto this vector. So A transpose B is actually extraordinarily powerful because what it lets me do is it lets me take any unit vector that I want, anyone, and then for any other vector, no matter how long it is or what its shape is or what its direction is, and project it down to see where it would land on that vector, right? Now you can imagine this getting even more powerful. What if I had another orthogonal vector, right, that was perpendicular to B, also unit length, let's say this was C, so C is also unit length. If I took the dot product with that, I would now know both coordinates of this A in a new fictional space that I've constructed, right? Instead of the X and Y axis being how things are measured, by taking both dot products, I would essentially create new coordinates for A, new coordinates in a coordinate system that I set up. So essentially this A transpose B allows me to measure any vector that I want on any axis system that I want, just by setting up two unit vectors that are orthogonal to each other, that are perpendicular, right? So imagine I want to do this. What are the coordinates of A in this new magical reference frame, this BC magical reference frame that I've constructed, right? Well, I just said what they were. They're A transpose B for the x coordinate. If this is my new x-axis, I don't know, maybe it's not. Maybe that's, I suppose this should be the x-axis because it's right-hand rule, right, going that way. So this is actually not quite right. Let's say that it's A transpose C, right, is my x-coordinate, and A transpose B is my y-coordinate. That's the new vector. And that tells me the coordinates of A in this space. Make sense, right? Okay. So hopefully you're clear on that. And again, you know, I worked through all of it to show you how that actually happens, giving you the right triangle and so on. But what you really, again, you want to internalize that, and you want to spend as much time as necessary to get familiar with these guys. But the important takeaway conceptually, right, is that measuring process. Okay, it's that measuring process. It's saying that a vector, right, dot a unit axis equals the coordinate of that vector along that axis. Make sense? Now this works even for the axes we already have. So if we were to actually take the x-axis and the y-axis and do this, we'd get the right answers. Why? Because what is the x-axis, right? What is the y-axis? Well, if we represented them as vectors, we'd get 0, 1 for the y-axis, right? There's no x component and it's going 1 in y. And for the x, we'd get 1, 0. Well, what happens if I dot product those with some vector in the space, right? If I have ax here and ay, what happens if I dot that with one of these? Well, you should be able to do that right away. You know it's ax times 1, so that's ax, and ay plus ay times 0, which is 0. So it's just ax, which is the x-coordinate of the vector in that space. Same is true if you did it for y, right? So this is like the universal measuring operator. It has a lot of other uses besides that, and we'll see them later on. But that's the one that we're going to talk about right now, because with that in mind, with that power, the old thing that looked so complicated, where how are we going to deal with this arbitrary wall, becomes trivial, right? Totally trivial now. So let's go back to our diagram that we had before and see if with the dot product we can now solve the problem that was so sort of weird before and difficult. Oops, get that in there, right? So what I'm going to say is for any wall, in order to do a reflection off of it, all I need to know is I need to know a unit vector that points out of the wall, right? Also called the normal of the surface oftentimes, right? So there's my reflection. And I'm just going to call that, I'll just call that W for now, right? We'll call that our wall vector. Maybe I'll call it our reflection vector. Do you want to call it R? I don't know, it kind of sounds like rotation. We'll call it R. And what we have to say is R, the length of R is going to be 1. R is a unit vector, okay? So now I take anything that comes in that I want to reflect. Any vector, right? So this is my V, this is my velocity, right? And again, I'm drawing it coming in here because that's the physical version of the diagram, but really any vector is, you know, if we think about it, it's at the origin, right? So this is actually my V. And now what I want to do is I want to reflect that around here. I want to reflect that around here. So what do I need to do to reflect it? Well, I said before that what I need to do to reflect it is negate its y component when it was lined up with the y-axis, right? So all we need to do now is figure out what part of it we actually would need to negate in this new axis system, right? If this were the y-coordinate. So how do we do that? Well, I just said I can measure any vector along another unit vector, which is what I have. So if I take V transpose R, right? If I take that, that will project me onto that vector, right? So V transpose R gives me this vector, well, actually, it gives me a scalar, right? It gives me a scalar, which is how long this actually is along that vector, right? So now the question is, that's the quantity I need to negate, right? I need to make sure my new V, my V prime, right, my new velocity, basically is the negative of that. It's going upwards. But this is a scalar quantity. It's just a number. It's the measure along here. How do I actually, I need a whole vector for reflection. I need to construct this whole vector. So what do? Well, it's pretty easy, right? If I were to start, here we go. If I were to start by saying, well, all right, I have my V, right? I now need to change it so that I'm going to get it so that it reflects through here. I just need to add something to it, right? That's going to move it up so that it will have that reflection. And I know exactly what that quantity is. My V transpose R is the length along R that this was, right? And that's going to be negative, obviously, because we know it's going into the wall, so that's going to be negative. So if I multiply that scalar times r, times the actual wall reflection direction, right? That gives me a vector. That gives me essentially this vector right here, right? That's actually the vector now, not just the length. So all I have to do to reflect this across it is just subtract 2 of those, right? Just to move it up to here first and then up to here second. If I just subtract 2 of those, I will flip the vector around and have it go out in the other direction, right? So again, just constructing it very much like it, just doing what I want to do with it. So if I take the old v and I subtract 2 times the quantity over here, right, where I've got my v transpose r times r, right? That will start at my v. That will figure out how long it is along the reflection vector. It'll move me back to the even line. This will move me back to the wall, this first one, right? And then by doing 2, I then move myself basically to the mirror position. And this was a bad drawing of where that would be. It would actually be like over here or something, right? So my new v prime is just that. That's the entirety. That's all I have to do. I just have to take my incoming velocity. I just have to subtract twice whatever that measure was along the reflection vector, and then move it in that direction along the reflection vector, right? Makes sense? And that is, of course, if I've done the math right. Like I said, I'm horrible at math, so anytime we compute something like that, we need to then go test to see if I'm right, because a lot of times I'll just make a straight-up mistake. Okay. You know what I just realized? I just realized my Linux has hung completely, which is unfortunate, to say the very least. All right. Well, that's all right. We'll go ahead and get that rebooting. It has not been a good week for Linux, ladies and gentlemen. It has not been a good week for Linux. My Linux crashes all the time now. It's very unfortunate. Anyway, so this is what we need to implement. And all we really need to do is anytime we want to bounce something, we can just go ahead and say, let's go ahead and define some unit vector in the direction we want to bounce, and we can bounce. And now we are not restricted to just bouncing off of things that are going to be, aligned with an axis system, which would have gotten us a certain, a certain degree of the way, certainly, right? We totally could have bounced off just the tile map edges using that. But as soon as we want to do something fancier, it would not have worked, right? Because if we want to have some kind of a slanted wall in there or anything like that, we'd be out of luck. All right, I'm going to go ahead and take 1 second here to go ahead and start the hex chat back up. So I will actually be able to see questions at the end. So sorry about that. Again, not the best situation for Linux. Let's see. Is it so hard, people? Is it so hard? It is apparently so hard. Okay, hopefully that'll stay up long enough for me to answer the questions. Okay, so let's go ahead and do that. Let's go ahead and just implement this. So I now want to do a thing where I compute that bounce. And in order to do that, I know that I need a dot product. So we'll open up our math routines and add one. So in line, again, it returns a scalar value, inner product. It takes 2 things, and I might just call this inner because it use it so often, it's pretty obvious what it actually is. And so the result here, again, very straightforward. It's just ax times bx plus ay times by. Okay, there we go. Return that there. And so that's our dot product, inner product, scalar product, whatever you want to call it. And that is what we're going to be computing to do our reflection code. And so if we want to reflect here, basically this is in the case of the tile point not being empty. I guess what we could do is say, all right, then if the tile point is not going to be empty, then we basically have to figure out what direction the wall was actually in, which we haven't actually done yet, but let's pretend that we do have that. So we basically have our r, again, this is going to be some value here. Which again is that r from this equation. And what we need to do is take our velocity, which again we have, it's the game state d player p. And what we need to do is reflect it about there. So what we need to do is say, okay, we've got the d player p, and the new d player p for this frame, or I guess, have we actually retired the point yet for this frame? We did the test. So I guess it'll just be for next frame, this will count. So we take that dplayer P. We're going to have to work on this player motion code a bunch, to say the least. But anyway, we're going to take that old dplayer P. We're going to subtract 2 times the inner product of whatever it actually is and our wall vector, right? And then we're going to multiply that by the wall vector itself, right? So there we go. That's the actual equation that we need to use. And oops, those were lowercase. They should not have been. I wonder if I should make those lowercase. It's a good question. It lines up better with the shader code if you make them lowercase, because shaders have .x, .y, that sort of thing, if that makes sense. All right, so what we need to now know is what actually is that. So let's hard code it first to make sure that we actually have our stuff working at all. So if we actually wanted to bounce off that bottom wall, that bottom wall is going to be obviously just the y-axis. So this should do the initial thing that we just sort of said was what we would do if we didn't actually have the dot product or any of that stuff. So let's see. There we go. Of course, that's pretty funny. Yeah. So there we go. No problems there. Seems to work pretty good. Of course, I'm accelerating against it, so I kind of there we go. Yeah, so that's pretty straightforward. Nothing much to see there. Now, of course, the problem would be if we actually do that, we would have the wrong, we would have the entirely wrong behavior because we're not actually computing the wall correctly. So what we do need to do is figure out some way to actually figure out what the direction of the wall is that we ran into. And I don't think we really know very much about how to do that at the moment. I guess we would have to sort of say, well, when we check these points, right, the new player P, the player left, and the player right, we need to figure out which ones of them are not actually allowed, because we don't really have much in the way of collision code at the moment. We'd have to figure out which ones of those were interpenetrating, and for whichever ones were interpenetrating, we would then have to figure out which direction the step was between the current position and the new position, like which direction we stepped in the tile map would tell us where the wall is. And this is one reason why, you know, like I said, later on, I don't think we're going to be doing any collision detection on tile maps because it's just kind of annoying, and I don't think we probably want to have like a more interesting boundary around things. So yeah. So I wouldn't basically put much weight into this particular stuff, but the bounce code is correct, and so let's keep going with that. Anyway, so let's say that what we do here is we take a look at these guys. I guess we could just say whichever one of these, yeah, this is kind of ugly, but let's just do it because we might as well, we're here. So we've got a bool 32 that's going to say, you know, I guess, well, you know what, I don't even need one of those. Well, I do, yeah, I do. Okay, so we'll just say collided. And again, this is really bad. This is not at all what I would advise doing, but I just want to, we're working on the wall code right now, so I don't really want to spend any time thinking about it. I just want to do something where we can get our wall out and go. And since we know we're not going to be doing collision detection this way eventually, it's not particularly interesting to me to think about it much more. So basically, if the tile map is not entered there, I'm going to say collided equals true, right? Like this. And then I'm just essentially going to do that same thing here. So player right, and player left. So I'm just going to take a look at those collideds, and if I did collide, then what I'm going to do here is say that there's a tile map position, call P or whatever, and that's going to equal in the case of collision whatever we actually found was the collision and trigger, right? Whoever actually collided. And this will let me know what actually caused us to not move, right? And so this now becomes collided. If we did not collide, right, then we can go ahead and do we can go ahead and do our stuff. And so that shouldn't change anything as it is, right? We should still be able to do whatever we were doing before. But now we can compare and figure out where our wall actually is, right? So if we want to see where the wall is now, we can essentially say, well, we know we collided, right? And so in some sense, we could reverse the sense of these so that we can get rid of that not there so we can actually see more cleanly. If we collided with something, we just need to figure out what our wall is. To figure out what our wall is, we then go, all right, We know col P is the thing that collided. So what we need to do is take whatever the player P is, right? Whatever the player P currently is, which is this guy. And we just need to see what direction he was trying to go in the tile map, right? So if you remember here, we have the tile map position. We have abs tile X, Y, and Z. So we just need to look and go, all right, if the abs tile X is less than the abs tile X here, then we know that this wall was a wall going in descending. The player was moving from like to the left, right? The player hit a wall to the left, and we could do the same stuff in all the directions. If it's greater than, and if it's that, so on. And since we can't really make anything collide diagonally at the moment, I guess we don't really need to worry about that case. But anyway, here we go. We can basically do, I think people were saying we could do this, right? Yes. So, given that we've got, what was the complaint? Oh yeah. Given that we've got that, we basically just need to define the wall for each of these motions. So in this case, I'm moving to the left, so that means the wall is like its normal pointing out to the right. In this case, I was moving to the right, so I have the wall pointing to the left. In this case, I am moving up, and so the wall is pointing down, right? Is that correct? Yes. Wait. No, it's less than, so it's moving down, so it'd be up, right, and then that. I believe that is all of them. Potentially undefined col P is used. Well, if it collided, we know that, well, all right, fine, we'll just do this. There you go. And we know that these cases can actually happen, but the compiler is being a bit persnickety there. So in theory, that should give us bouncing off of all the walls. Yeah, there we go. Right. And so now we're just a bouncy little fellow who's pretty happy about his lot in life, very determined to go around bouncing along things. And the faster we go, the harder we bounce, which is exactly what we wanted in terms of our behavior. Now, like I said, if we wanted to, we could make him bounce a little softer off things by basically adding a coefficient in there. It's called a coefficient of restitution. The coefficient of restitution would basically be some number less than 1 that we would multiply our vector by to reduce how far out it went. And so that's really all that is. Yay! Bouncy fellow. Okay. All right. Sorry, I'll stop bouncing around in a second, but it's kind of fun. Yeah. Now, in theory, we don't really handle the diagonal very well, and you can kind of see that. So you can see what kind of happens up in there, and that's because we only really handle bouncing off of one or the other at the time. And that's because, again, like I said, I don't think the tile maps are really that interesting way to do stuff. So I don't think we'll handle that eventually that way anyway. But what we could do if we really wanted to start doing, if we really wanted the tile map collision to be the way we did collision, what we could do is round those off a little bit, pretend they were rounded in there a little bit, and have a nicer collision there. But it's still, it's fine. I mean, it works. It's just, it's not pretty, right? Yeah. All right. So now I got another question for you, because I've given you I give and I give, stream. I've given you everything now. It's time for you to give back. All right. You're the man now, dog. What I want to know is basically, I told you all this stuff. I told you about the dot product, right? Instead of keeping it a secret, it could have been only me that knew the dot product this whole time, and only I can do all these awesome things, and now you know it too. So tell me, with that power, how would you now do something else with the collision response? Let's say what I want to do is have him have the standard, the more familiar kind of Quake style movement, where if my guy runs into a wall, then basically he just runs along the wall like that. So instead of him bouncing out like this, he just kind of goes like that, right? Smoothly along it, right? How would I do that? Now, there's a trick to this. One part of it I expect you to get, and the other part I don't expect you to get, because one of them is a programming thing, and we haven't talked about that yet. But you should be able to do the math part of this. Does anyone know? Anyone? Well, you're behind on the stream anyway, I know that, so I can't really expect you to answer right away. But the reason that I think this should be easy, and if you want to pause the stream and try to figure it out yourself, I highly suggest it because it should be. is that I already told you essentially exactly what you need to do this. Instead of minusing 2, you could just subtract 1 version of this, and that would bring you right up to the wall, right? That would bring your velocity so that it was just along the wall. So what we could do is instead, instead of it being -2, right, I could just make it be -1. Now, like I said, there's another trick to this, though. So if I do that, there's another problem that we have to solve, that it will expose, that we really should have solved before, but, you know, we didn't really have to in that case, right? Now you'll notice when I come on here, right, you can kind of see, well, you know, it's not as pronounced as I thought it would be. It sort of happened a little bit there, but it's not as bad as I thought it would be. Yeah. All right, I take it back. Maybe we don't have to fix it. I felt like we would have to fix it, but I guess we didn't. But you can kind of see now what happens is exactly what I expect to happen, which is that if I'm going diagonally down, you get that grindy wall thing that you're supposed to get in video games where you go a little slower against the wall when you're pushing into it, and you go faster if you let up, right? Which is exactly what we want to feel. That's like a good game feel thing. And so that's, right, like totally trivial. But what I thought should have had to happen, and there you can see him kind of sticking a little. There we go. I was going to say, it should happen. Hopefully you can sort of see how he was sticking there a little bit occasionally. There we go. Right there. See how he stuck? So that's the problem that I was alluding to that we had to fix. So I was kind of glad that that happened, because I was like, well, I told you there he is. There he did again. Right? You see that sticking? Why is he sticking? What's going on? Right? What's going on with the sticking? I can hear you saying it. What's going on with the sticking? So the problem that we have, and this gets sort of to the heart of collision detection at some level, and we'll never totally escape this. I will show you the ways in which we solve these problems in practice, but we will always have to keep thinking about it. There's no magic bullet. Is that in the real world, collisions aren't some instantaneous thing. Everything is happening kind of continuously, and again, it's all atoms, and they're all working together, and this sort of stuff. And collisions are this elastic thing where something deforms a little, and dents a little, and moves out, and whatever, right? We're simulating collision like it's this fixed step thing, right? And so what we wrote our code to do way back when, this is not something we wrote today, but what we wrote our code to do way back when was go, okay, I'm here, you know, here's my dude, right? So here's the hero, and he wants to go to here, right? But this is inside a wall. And so what we did is we disallowed the move. That's what we did. But what that means is now, when we have our code that's trying to do this stuff when we skate along the wall, we get into a problem where if the user is pushing down into the wall like that, right, we can correct that velocity, but we've already denied the move. So the hero essentially doesn't move on that frame, even though we've corrected his velocity, right? So what we really want to do is we want to see if he would have collided, and if he would have collided, we want to correct his velocity and then try to move him again. And you can see why this is a bit of a nasty cycle, because then your very next question should be, and legitimately should be, mind you, what happens if he collides then? So you're kind of in this nasty situation where you have to deal very specifically with the discreteness of everything and go, oh, I've kind of got this nasty problem where I've got a lot of different sort of concerns there, right? And so what we could do is very simply, like, you know, we could try twice and then give up or whatever. Like, there's different things we can do. We'll be looking for... There's a really interesting way I solved this on the witness that I hadn't actually seen anyone talk about before, that I've sort of considered doing in Handmade Hero, but I don't know if it's the most appropriate thing for it, so I don't know if that's a good solution or not. But we will look at various solutions later when we do our full collision detection. But so for now, we'll have to do something, you know, that's somewhat janky, right? That's not the nicest thing in the world. And so basically what we would do there is say, okay, if we correct our velocity, let's try using that velocity on this frame, right? And again, that's not exactly correct either. Okay, so I'm going to go ahead and wrap this in a for I loop. We are going to do the new player P, right? We've got the player P offset that comes in here, which we try adding. And then we go ahead and say, once we've actually computed that dplayer P, we're going to, right, okay. And so what we need to do now is say, all right, now that we've actually computed a new dplayer P, we need to be able to try again this basic process, right? So I'm trying to think, this is a reflected vector that's happened after the acceleration was tried. And do we want to do, how do we want to do that exactly after we've clipped that velocity? I guess we just want to move him by that velocity that we actually have left. So I guess I don't want to solve this in this stream because here's what I actually want to do. And so maybe we should save this for tomorrow because we just don't have enough time left. What I actually want to do is I want to actually sort of show a slightly more correct collision response here, which is when we have this motion and we find that we intersect, I want to back up to the point where we hit and put the guy there and then correct his velocity and then step it forward, right? I want to do something like that. And so I would rather do that potentially. It's such a tough choice here, guys. Or maybe I'll do the thing I did in the witness. All right, so you know what? Let's table this till tomorrow because we don't have any time left. Let's get ready for the Q&A, and let's just say this is a to be continued that we will talk about tomorrow. And I'm going to think about which way I want to solve it right now. Because I think I might want to actually try the witness way because it's actually kind of cool, and I think we can just do it here. And then whether or not we can actually do it a little later on, I'm not sure. Because there's more to the witness way than the way that I would be able to do here. So let's just table this for now. It's 8:59, and we will pick it up again tomorrow. So we can start the Q&A, and basically what I would like you to do is, if you could, write in and put your questions with a Q colon in front of them so I can see them. Is there a way to speed up the draw bitmap code? I'm trying it on my laptop and it doesn't hit 33 FPS. There are a lot of ways you could speed up the draw bitmap code. I don't really know that I want to talk about them right now, though, because one of our very first tasks after we sort of finish getting our basic movement, basic gameplay stuff in over the next couple of weeks is to write the renderer. So I'd like to save it for then because we're going to actually write a whole renderer, and that'll be the time when we'll look at it. If you're looking at just the basic thing that you might want to do, if you haven't already done it, if you're just trying to make it run faster, what you could do is turn on optimization, right? So if you go in here and you look at this, you see optimization switch is O2. If you put that O2, if you just put an O2 in here, that would compile it to probably run quite a bit faster. So if you haven't already done that, you'd want to do that. All right, it looks like we are done with questions. Do I have any more questions? If so, wow, this is an early Q&A. Was the witness collision trick to try and maintain the distance traveled? Uh, no, the witness collision trick is to do movement as a search problem instead of as a physics problem. much to see there. Now, of course, the problem would be if we actually do that, we would have the wrong, we would have the entirely wrong behavior because we're not actually computing the wall correctly. So what we do need to do is figure out some way to actually figure out what the direction of the wall is that we ran into. And I don't think we really know very much about how to do that at the moment. I guess we would have to sort of say, well, when we check these points, right, the new player P, the player left, and the player right, we need to figure out which ones of them are not actually allowed, because we don't really have much in the way of collision code at the moment. We'd have to figure out which ones of those were interpenetrating, and for whichever ones were interpenetrating, we would then have to figure out which direction the step was between the current position and the new position, like which direction we stepped in the tile map would tell us where the wall is. And this is one reason why, you know, like I said, later on, I don't think we're going to be doing any collision detection on tile maps because it's just kind of annoying, and I don't think we probably want to have like a more interesting boundary around things. So yeah. So I wouldn't basically put much weight into this particular stuff, but the bounce code is correct, and so let's keep going with that. Anyway, so let's say that what we do here is we take a look at these guys. I guess we could just say whichever one of these, yeah, this is kind of ugly, but let's just do it because we might as well, we're here. So we've got a bool 32 that's going to say, you know, I guess, well, you know what, I don't even need one of those. Well, I do, yeah, I do. Okay, so we'll just say collided. Again, this is really bad. This is not at all what I would advise doing, but I just want to, we're working on the wall code right now, so I don't really want to spend any time thinking about it. I just want to do something where we can get our wall out and go. And since we know we're not going to be doing collision detection this way eventually, it's not particularly interesting to me to think about it much more. So basically, if the tile map is not entered there, I'm going to say collided equals true, right? Like this. And then I'm just essentially going to do that same thing here. So player right, and player left. So I'm just going to take a look at those collideds, and if I did collide, then what I'm going to do here is say that there's a tile map position, call P or whatever, and that's going to equal in the case of collision. At what's going on at the moment. So where we left off, we had just kind of started playing with the equations of motion. I showed everyone how to do both types of sort of handling of when somebody runs into something. We did a bounce version where the guy would kind of bounce off of it, and also a deadening version where he just stops. And what we wanted to do, of course, is it doesn't feel very good if he just stops and sticks. So what we wanted to do is have him keep moving along the edges when you kind of grind against them, because that's the standard thing to do in games, is that, you know, it doesn't feel good if you just stick against a wall. You want to kind of glide against the wall so that you keep moving with whatever downward velocity you should have had when you come against like a vertical wall, and it's only the horizontal velocity that gets eaten. But we have a sticking problem that I explained yesterday, and that is that we haven't written our loop properly, I'm sorry, it's not even a loop. We haven't written our game update for the character in a useful way, and so actually what happens is we get a sticking problem. And the sticking problem that we get is that if you imagine that this is the wall, right? Here is the wall, and the hero is coming towards the wall. And the way that we wrote our quick stuff when we were kind of just testing our tile map code out, we wrote in some little quick test code to collide the guy against the tile map, but it's not very sophisticated yet. And so all it was doing is it moves the guy to the new location, looks to see whether or not he could exist there. Like, is he in a wall or not? And if he's not, it accepts the move. If it's not, if he can't stand there, then it denies the move completely. And it means the guy will just stay where he is on that frame. Which leads to a nasty sticking problem, which is, first of all, you lose at least one frame when that happens. But if you got into a situation where the guy was right up against the wall, and then when we correct our velocity, and then the acceleration for a frame puts it back inside the wall again, he could just stick there indefinitely. And it's kind of hard to get that to happen floating point wise. It's a more of a rare case, but you can see that it does happen occasionally. Did you see that stick? You can kind of see how it, like right there. So it definitely can happen. It's just not as common as maybe I would have thought it would be, possibly a little more common than it actually is, but it's not as common. But it still happens, right? And so it's not something that we want our final code to have. And so since the whole point of what we've been doing these past few weeks, in addition to, of course, learning math and learning about sort of the stuff that we need to do, is we've been trying to come up with all of the things that we need our game engine to do for us. And obviously, this is one big area of the game engine that we want to work really well, which is how the player movement is handled, how the collision detection is handled. And so it's important for us to think a little bit about how we want to handle this. Now, there's two ways that we could handle this that I kind of alluded to yesterday. There's probably more than two, but I'll at least cover two. One is kind of the standard way of handling it, and the other is sort of the way that I'm not sure if anyone does it this way, but it was a way that I did it on the Witness recently, and which I think is pretty interesting. I'm just not sure if it can work in the larger scheme of this game, and so I'm not sure if we want to do it long term, but I was going to mention anyway. So typically, what games will do, and this gets into another problem that we had. So, well, we didn't really have the problem, but we would have potentially had a problem, which is that if you think about what happens in this kind of a scheme, which is like check a new location and then move there if it's free, you get into a situation where theoretically, and we didn't ever construct any cases that could really do this, but theoretically, if you had a very thin wall, right, you could teleport through the wall, because if this is the region that you can't stand, but you could stand out here, then it's only checking to see if the final location is okay for the guy to stand at. And we know that we're never checking in this whole distance that he moves, right? And so that's also another problem that we are not dealing with, that we might want to deal with in the final version of the game, right? So it's something to consider when we're thinking about how we want our collision detection to work, is whether we're worried about that, right? And since our goal here is to create a professional quality game, I feel like we should handle that, even though we may never actually have any maps that actually have this problem. I think it's the right thing to do to show how you would handle it properly. So anyway, let's suppose I'm back to my standard wall case. So a typical way that a game might solve this problem is if we have this movement, right? Then the first thing we would do is we write a collision detection routine that actually will check to see when collisions occur rather than just whether they occur, right? So rather than taking a new position, which is here, right? This is our P prime, this is our P, this is our old position, this is our new position. Rather than just checking P prime, it will actually check essentially an extruded volume. It will test this whole volume here. And since we're in 2D, it's more of an area than a volume, but you know what I mean. It will test that against everything in the world as sort of like a geometric operation, and it will find, even if there was a thin wall and there's nothing on this side, it will find that intersection in the middle, right? And more to the point, for our sticking problem, it will find the place where the intersection first occurs. It'll say, oh, okay, this is the point at which he hits the wall. And so when you do that, you then have the ability to place the guy at the location where he was going to hit the wall, right? Instead of only having the choice between the new position and the old position, we now generate a third position, which actually becomes the P prime, and we throw that one away and say, here is the place where he actually would have ended up, right? But doing that is still technically going to cause sticking problems in two ways. One, we haven't talked about what we would do with the velocity problem yet. And the other is that we would, when we do that step, we now have thrown away a bunch of the player's actual momentum, right? Because the player actually probably should have ended up here, because they still had enough downward momentum to get all the way there. So the only thing we really wanted to throw away was this momentum that was going into the wall, right? So we want to basically move the player to here as the movement, not to here. So oftentimes what they'll do is they'll resolve these things in sort of a loop, like I was saying before, where they'll move the player and then they'll take whatever the remaining, they'll correct the velocity, just like we were doing yesterday. They'll take whatever remaining time step there was, because you know how much time it took to get here, right? You know how much of the time step it took to move you there. You'll take how much time it was, and then you'll try to move them in the resulting velocity direction that's been corrected for the wall to see if you can do that, right? And you can see that this is kind of ugly because this is essentially a search in T, you might say. It is a iterative loop that is basically searching through time for answers. It's doing some part of the delta T here. So, it's some fraction of this. It's 1 over A, which is some fraction of that time step it's using. And then it's trying to use 1 over basically the rest of it, this kind of thing. It's using the rest of it to move here. And this just gets kind of messy because searches in T are very difficult to bound in any real way. Because what if I had a very complex sort of wall situation at the end here, right? And this is kind of exaggerated, but just to sort of show you what I mean by the problems. What exactly should be happening when he goes against here, right? Am I going to do this thing where I actually take tons of time steps, tons of little portions of the time step, and have to do like 8 resolutions of my collision loop to move the guy all down through there, and is that really a good use of time? Is that the way that I want my inner loop there to be running? And it's unbounded in some sense, right? Like I don't even have any idea how many of these I would have to do in order to actually get the guy to resolve his position. And I feel like, you could imagine this being the case with a wall that was curved. Like let's say I wanted to do a rounded wall like this. Well, if I have a rounded wall and I'm pushing against the wall like this, you could imagine this being the very worst case where it keeps having to correct that velocity. And it's almost like the number of iterations goes to infinity because I keep having to move a little bit down, a little bit down, a little bit down, a little bit down. So when I correct, because remember the way we correct is we look at that normal to the wall and we correct this way. So we correct it so he's only moving lateral to the wall. But lateral to the wall in a curved wall will constantly still be pushing you into the wall, right? So there's all these problems with this approach. And that was really what led me to look for a better solution than I'd seen presented before when I was working on the witness. And I'll tell you briefly right now the solution that I came up with, which I really like, and it works fantastic on the witness. I just don't know if it's appropriate for an action game. So I'll sort of say what it is. So what I decided to do was say, well, search in T is not good. Let's not do search in T. Search in T is unbounded and unpredictable and doesn't work very well for a lot of scenarios. And what a lot of games do is they just cheese out and either just do some number of loops, or they do some cheesy stuff where they kind of like don't handle a bunch of those cases. Like if you grind into a curved wall, you just do something awful. So these are just, search in T is just busted. It was my official opinion. So what I decided to do was, let's turn a search in T into a search in P, right? So instead of searching in time, right? Instead of searching in time, let's search in position and see if we can find a position that will work, because the search in position is much more easily bounded and much more easily understood, right? So what I do in the witness is I think about whatever I have in terms of geometry for the collision. So let's say I've got this sort of a thing here. Basically what I have is a grid that is used, that is tessellated out for a bunch of reasons that would be clearer if we were actually talking about the witness. But basically, like, it's got a tessellated out thing that's very fine resolution, that sort of says exactly what the collision geometry looks like at any given point. And it knows, basically that you can't be in here like that, but that you can be in here, right? And so what I do is, when somebody is moving in this space, what I do is I go back to the old scheme, which is just, let's just take the location of the guy that he would be at. And then what I say is, let's search in position, because I know that however long this is, I can basically make a rectangle around however long the span is that he moved in that time. Let's just search in the grid for the closest point to wherever he would have ended up, right? So that just turns it into a nice bounded search where I know I'm just searching a predetermined number of cells, and in each cell I just look what is the closest point in this polygon to this destination point. And that always gives you a 100% perfect, 100% predictable result for that metric, right? It's really, really nice. And it's buttery smooth. You never get caught on little weird edge artifacts, and it even has the ability to do something that I consider beneficial in the witness, but that I wouldn't necessarily consider beneficial in this game. I'm not sure, and that's why I'm a little hesitant about it. But basically, it has the ability to glide over transient errors, right? So if you have a wall that looks like this because of some weird computational geometry stuff, like the artists, had some walkway that was kind of sticking in there an errant way, and you got this sort of thing, and I'm trying to grind along this wall. Well, if you were actually grinding along this wall in a normal engine, when you got here, you'd stick on this tiny little microscopic bump that you may not even really be able to see, but it's in the collision geometry, right? You'd stick, and it feels crappy, right? But in this scheme, because what it's doing is doing that search, it finds the fact that you could have moved around that, and allows you to tunnel through things like that if you could have walked to them, right? So it's buttery smooth on edges, way better than anything else I've ever seen. And it was really, really good when I switched to using this system. And so I was pretty psyched about that, and it feels awesome to do. So search in P is actually way better than search in T for collision detection. I don't know if anyone's ever actually... I don't know if I'm the first person to have done that. I assume not, because usually anytime you do something, someone's done it before, you just haven't heard about it. So I don't know if there's more write-ups about that somewhere, but that's a pretty... I think that was a pretty complete explanation in terms of just what you would need to do to write it. So really, this is what I would like to do if we could do it. I'm just not sure how appropriate that is for an action game, because producing the searchable set is actually a relatively hard problem, right? You have to be able to search your geometry. And I don't know if we've got lots of things that are moving around and whatever, I don't know how easy it would be to really produce that searchable set very, very easily. Because remember, we have to, like, let's say we had something where, this is what a cell would look like, because there's a guy, a guy with cylindrical collision or something who's in there, and we want to know what the closest point is. It means you have to know how to do closest point on something that looks like that, right? And you can do stuff where you kind of tessellate it out and don't exactly do it that way. But point being, it's a system that's much easier to implement when you're talking about a world that looks like the Witness, where everything is stationary and known, versus something in an action game where there's lots of like small things moving around and that sort of stuff. It's unclear necessarily how you turn things into a search NP problem in an efficient way, right? Okay. So that is basically the dilemma that I face now, is this is what I pretty much know to be a better way to write things. But I've never, since I only just came up with it on the Witness, I haven't had any experience trying to do it in an action game. I don't know if we would struggle to make it work well in terms of producing the search. And so this is the way that's kind of a little more tried and true. And I really don't know which one we should do. For our current setup, where we have a tile map and the tile map is actually definitive, because right now we haven't done any of the other stuff where we've got guys moving around, and we haven't done any of the stuff where we populate the tile map with collision geometry and then stop colliding with the tile map and collide with the actual things that are in the tile map or things like that. We haven't done any of that stuff. Search and P would be trivial for us to implement right now, and would definitely be the right way to go, but that doesn't mean that it would be the correct way to go, at the end. So I don't know what to do. I really don't. It's a very hard question. Since I believe this to be the superior method in general, my inclination is for us to just do this and say we'll struggle with it a little bit when we start to do the more complex stuff, but maybe that's just what we should do, and it should be a little bit of an exploration. And so we'll start with this as the way we do things, and then as we see how it goes out, if we need to turn to something like this, we can. But at least this, I believe, is personally, I think, the more stable way to do it. So really all we would need to do to implement that in our current system, right? Because our current system's a tile map. It's totally rectilinear, and we haven't gotten to the point where we have more complicated collision geometry in there. So in a tile map, if you were actually doing collision detection on a tile map, then there's no question that you would do it this way, because it's really simple. All we have to do is take the guy and his new position, right? All we do is we say, we've got the guy, we've got his new position, and all we really need to do is like make some conservative boundary around that. So we just make some rectangle around that and say, what are all the tiles that are touched by this rectangle, right? And so in this case, it would be, these tiles here, right? Like that. Then what we do is say, all right, for each one of those tiles, we just loop through the tiles in like a for loop straight away. And we say for each one of those tiles, right, we just need to kind of go, well, actually, I guess you wouldn't do a for loop. Never mind, that's wrong. We then do a flood fill. We say, for this tile, which of the tiles, could I actually get to? Like, which of these tiles can I get to, right? So can I get to this one? If so, add it to the set. Can I get to this one? Add it to the set. Can I get to this one? Add it to the set, right? Can I get to this one? Add it to the set. So the ones that I can walk to, add to the set, right? Because you only want to get to ones that you actually could get to. So you need to know that there is a path to them from your current location. So you basically flood fill outwards, and you don't have to flood fill past whatever you set that boundary to, right? Once we've done that, we then check all of the tiles that we actually picked up there. All those tiles that we actually picked up, we then say, okay, for that tile, is it solid? If it's solid, we don't consider it, because you can't stand there. If it's empty, then we say, is the point that we're trying to stand in, the new point, is it in there? If it's inside there, then that's the point. We can move there. Just go, right? And we're done. If it's not, we say, okay, along the edges of that guy, where is the closest point, right? On each of the edges, where is the closest point to this point, right? And that handles the case where you're actually standing right on an edge, right? And we produce that point and say, okay, then that's the closest point for me. We do that for all of the tiles, and for whichever tile at the end has the point that produced the point that is the closest to the one that we wanted, that's the move that we accept. That's it. So it's really, really, really pretty basic, if that makes sense. All right. So that's it. Yeah. I guess that's really the entirety of the algorithm for a tile map. It's really pretty straightforward. And so, yeah, we can just go ahead and do that. And we don't even have to really do the flood fill if we don't want to at this particular point in time, because we have simply connected spaces. We could just do it without doing the flood fill. But the reason to do the flood fill is just that, well, like, you know, let's say that I've got my guy, right? And I want to move him. Oh, there's one more thing there's one more thing that I do have to actually talk about. That makes this actually harder, and it actually makes everything harder. It's one thing I should talk about. It has nothing to do with this scheme. But the reason for the flood fill is, let's say that there was a wall here and a wall here. Then technically, like, we're not supposed to be able to move through that little that little part in the corner. So if you just checked each of these tiles without actually doing the flood fill to see where you could go, you would think that you could just move directly to there, right? But you don't want to do that because there's no way to actually get to that square from here. And so that's why you do the connectivity thing, to make sure that you actually could walk to that square before you accept any points that are in it. So here's the problem that I was talking about, or that I was thinking of. So the other problem that we have with any collision scheme is currently we don't really have an answer for what we're doing about the fact that the guy is not a single point, right? So any collision scheme that we start to work with has an extra problem to deal with, right? Which is that whatever it's doing, it has to deal with the fact that the guy is like a fatty, right? The guy is like, you know, he's larger than a point, you know, right? He's how do I, where's my, there it is. We were checking basically this line is what we were saying was the guy. But eventually we probably want him to be like more of like a circle anyway, like sort of this region that I'm kind of demarcating here would be his collision region, that he would bump into things. And so right now he's infinitely thin in Y, but he's thick in X, which means it's easy for him to fit through doors this way, but harder for him to fit through doors the other way, right? Like if I go, let's find a door there. So if I go through this door, it's harder for me because I can always hit an edge like that. And so that was just, I mean, we haven't really done any thinking about any of this stuff, but that was what we had sort of done, is made it so that he wouldn't, you know, clip into things. So turning him into a point is another problem. And the reason that that we would want to turn him into a point, the reason that we'd want to think about him as a point instead of as a sort of a circle, is it's much harder to collision detect with a circle. For example, if I have a wall, you know, and I want to know if the guy hits the wall, if he's a point, right, then I'm just talking about checking a line segment against another line segment, right? So I'm basically checking for the intersection of two line segments, which doesn't sound like a very hard problem, right? But if he's a circle, now I have to check an extruded circle, right, versus a line segment, which is definitely a more, you know, a more serious problem that you would have to solve, right? So in the first scheme, if for search and T, this is definitely a problem, right? Definitely a problem, because now you have to have a more serious collision routine there, and you know, that's a bit rough. So similarly, in our scheme that I was proposing we do, which is search and P, for search and P, it also is a problem just in a different way. And the way that it is a problem is that if my guy has volume again, right, if he has an area, then that routine where I check for the closest point is a little harder as well, right? Now, it doesn't happen to actually be harder in just this one isolated case, meaning the thing that we're going to implement today, it's actually pretty easy. The reason it's pretty easy is because if the guy is just a circle or an ellipse or whatever, then all we really have to do is when we're considering the rectangle that he could be in for finding the closest point, instead of using the whole rectangle, we just look to see if the square on a side of the rectangle is filled. And if it is, we just treat the rectangle as if it was the ellipse's the radius in that direction away from the filled area, right? Like that. And again, this is just another way that search and P is superior to the other method, is like, this is way easier than trying to do that continuous collision detection, yet it handles the continuous case just fine. You will never tunnel through anything as long as you do that flood fill pattern. So it is a little more complicated than I originally said, but only slightly when we do it this way. But you can see when we go forward why it will complicate matters to have him be a circle. Because let's say that we had some arbitrary collision geometry, right, that we were colliding against, and now the guy is a circle. Well, doing the closest point, figuring out what the closest point in the walk space is to here, is definitely harder now that we have to consider like this sort of fact that his closest point region to search is like this thing that looks like that, and we have to determine that. Like you can see this is really ugly now, like how to do that. So if he was just a point, we would just search along the edge of the collision boundaries anytime we hit them. That's a lot easier than trying to figure out how far away we would have to be for our circle to fit. It's not even as simple as just thinking, oh, I'll take a point and move it out, because you never know, there could be a sharp bend where moving it out from there actually still makes you collide with some other piece here. So it's definitely something to think about. This is also where Minkowski, the Minkowski shape algebra stuff comes in potentially, which we might use when we go to stuff that's more complicated like this. But for purposes of speccing out our engine, this would be fine, because if we say that we want to go with search and P at least at the beginning, then that at least gives us a good way to define what our engine needs to do, which is the whole point of all of our explorations now, which is that all we need it to do is be able to give us back with a P and a P prime, give us back the closest P that we could have gotten to from there in the connected space. That's a very easily defined problem. It's very clean. The API is obvious. So all of that actually does exactly what we need it to do for now, which is tell us what the sort of API is to our engine, and that will allow us to know exactly what problems our engine does have to solve when we write it. Okay, so hopefully everyone's pretty clear on that. So how do we write that? Because really that's just a bunch of code, right? There's not much math involved there, really, in terms of what's going on. So all right. Let's write it, and let's see what's going on here. So right now, what we're doing is we have this is tile empty, or whatever it is that we're, oops, not it tile, is tile map point empty, right? This is how we're doing it. This is our routine. And so what I'd like to do now is sort of totally change the nature of what we're doing here. I'd like to basically say, all this stuff that we were doing before, this stuff is over. It's done, right? It's not the case anymore. We're gonna get rid of all of this stuff that we used to be doing, like that. And honestly, this guy could have been outside here before anyway, because this is always true. Our on same tile. All we really need to do is say that this is an old player P, right? And a new player P kind of a thing. So what I'm going to do here before I if zero it out, let me just actually change it to do that, so that our post execute stuff is still going to work properly. So basically, I wanted to know if he's on the same tile. So I'm going to set old player P when we first come in here, right? I'm going to set old player P to be equal to the position that he started at. So when we come right in here, just to begin with, I'm going to set the old player P, right? Old player P equal to game. That game state. Remember, we've got his player P here. I'm going to set it to equal to that player P, right? And actually, you know what? I'm going to do that even outside here, really, because this is the part that updates where the player is, and then the part that responds to that, let's just do that entirely outside, right? Because all of this stuff has nothing to do with that, right? That's all stuff that can happen out here, right? So what we want to do is say if the old player P and his his new location, right? What I want to do now is get rid of that use of new player P at all, right? I want to directly operate on the game state version of the player, right? And so let's compile that and just make sure that we can do that. So this is tile map position. And let's take a look here. What is this saying? Diff multiple. Oh, do I have another function called diff? I do. Oh, and that happens to be the same. That happens to be the same diff. So really, all I need to do here is just update that diff. That's pretty funny. Yeah, because that's funny. Well, what are you gonna do? All right. So let me just verify that I've still got this guy working properly. So off we go, and that looks okay. He can still go up and down the stairs. He still runs into walls, as he should. So we're all good there. All right. Oops. There we go. And so I don't know, like this is starting to get to the point where we might. This is starting to get to the point where we could think about starting to pull it out too. You can sort of see it breaking out into some obvious pieces, like those parts that I just moved out there. You can kind of see that there's two separate, logical things that's happening, right? There's this update that happens after the player's done that kind of handles a bunch of stuff. And so this may be a good thing for us to move out now, because that's going to be kind of this is basically a update function that updates the sort of the state of the game based on where the player moved and the camera. We might want to consider moving that out to a new function. I'm not sure if we do yet. Hard to say exactly what that's going to be, but like I'm going to put a note in here: update camera and player low z based on last movement, right? And then here we'll get render. So I'm just going to start to divide these up, and we'll consider at some point whether we want to break that out, because we're getting closer to the point where it looks like we can start to see, real chunks that happen. And by the way, this is a good point to mention this. Somebody was saying on the forums a while back that they felt like the code was too messy, and again, I really want to stress the fact that I don't really want to try to tell people that the way that they code is wrong, because, I feel like that just leads to a lot of pedantic arguments that aren't particularly constructive. But what I can say is nobody, in my mind, nobody should be thinking that this code is messy. This code is exactly what it should be. It's code that we are writing to figure out how we want to structure our program. And if you're spending time right now thinking about how to make this code not messy, whatever that means to you, then essentially what you're doing is you're wasting time, right? You're spending time that should have been spent thinking about the problem, thinking about the code. And the end state, the end goal of your program is not to have clean code. It's to have good working code. Cleanliness has nothing to do with those things. If you have the ugliest code in the world that someone would look at and call very messy, but it has no bugs and runs great, then it didn't matter, right? And so to the point that we care about how clean code is, we only care about that as insofar as it has an effect on our end product. And what we know right now is what we're trying to do is just define the structure of the code. So none of this code will ship in the game, or if it does, it's because it got pulled out and like changed around a little and, put in its proper place. And so we know that it will clean up over time as we know what it should be. But prematurely cleaning it, it's actually worse than just wasting time. It may lead us down wrong paths and end up making us have to do gyrations to make stuff work together because we've segregated it in a bad way too early on. And so I really want to stress that fact that like if the way you look at code is that you think of it as messy or clean, that is a very bad habit in my opinion. And so all I can really do is say as strenuously as possible, stop thinking that way. Instead, think about the problem you're trying to solve. When you are done and to your satisfaction, solving that problem in however messy a way as you can, then that is the time to start thinking about cleanliness of code. And what we mean when we say cleanliness of code there is, can I find the bugs in it easily? Is it easy to read and understand? Is it easy for me to reuse in the places that I need to reuse it? Those sorts of things. And never some set of prescribed things that somebody said was clean code, because there is no such set. There is no set of rules that tells you whether a particular set of code is clean based on what the code looks like. It's only based on what the usage looks like and what the debugging process looks like that actually tells you whether a piece of code is clean or not. And I really can't stress that enough. It's a big difference between good programmers and bad programmers is whether they understand this, right? And that's, like I said, it's my opinion. Nobody has perfect metrics for code, so we don't know who's right about those things. But all I can tell you is in 30 years, I've never seen something truer than what I just said. All right. So moving on from there, from that little public service announcement, what I want to talk about now, right, is sort of radically revamping what we're doing here to something much simpler and much better, right? So we still have our physics stuff up here. So this is computing the player velocity, right? And what we want to do now is right here, we want to sort of if-zero this out and say the old way that we were doing stuff, that's not going to happen anymore. That's done, right? That's over. And we're going to do something else that's going to be better. And I'm leaving that in for now just because we might want to switch to it to see what's going on, right? So that's all good. All right. And then what I want to do is say, okay, let's go ahead and say, let's do that thing that I was talking about before. And for now, we'll just do it without any concern for anything. We'll do it in the worst possible way, and then we'll refine it a little bit. So I'm just going to go ahead and do a for I loop around, basically in that sort of region where the player is and where his destination point is. So we're going to basically say, I'm still gonna keep this part for now of the physics, right? So we produce that new player P. I'm gonna keep that, and I guess we want to do this. So, but the rest of this stuff where we do all the collision texturing and the testing, I'm not gonna use, right? So what I want to do now is I want to basically loop over the search region in tile space, right? So I want to be able to go over each individual tile there in X and Y. So I'm going to go ahead and do that, and we'll take a look at handmade tile.h here. I'm going to go ahead and do that and say that, min tile X, max tile X, like so, abs tile X, like that. And I think, so there is one kind of nasty thing about this. This is kind of, yeah. This is one of those things that's like, it's unclear whether we should change it going forwards. And I've thought about it many times on the stream when we've been doing stuff, basically the unsigned versus signed integer thing. So there's a nasty thing here that happens where we're right on the edge of a tile, where let's say that we were, let me just, I'll get this out there since I've thought about it multiple times and I've never mentioned it on the stream. I'll just say it here. So let's say we happen to be at tile 0, 0, right? So this next tile here is, tile 4 billion because we wrapped around, right? If I want to do a for I loop over these tiles, there is really, it's hard to write that loop cleanly, if that makes sense. Because you can't do a less than. So you have to kind of do an equals to, which maybe is okay. Sorry, not equals to. Because if you think about it, when you go back here and I start looping over this guy, when I loop over him, we're going to see that he's already greater than the stopping tile, which is the one that we were looking at over here, because of that wraparound of the unsigned integer. So I don't know, I'm just going to go ahead and keep on with the current way that we're doing things and see. I've thought about it a couple times, but basically we have to do this like that kind of. We always have to do a not equal to 1 past the max tile, because that's the only thing that will actually work when we do this loop. We can't ever really check for less thans, even though that's the more easier and natural way to think about doing the loop usually for me. We have to do these not equal to's because we might be right on that boundary where we're wrapping around, if that makes sense. We don't have to do that. We don't ever have to let the world wrap around if we don't want to. But I'm saying if we wanted to actually make the code correct so that you could have a full giant 4 billion loop for some reason, 4 billion tile loop, if you really just wanted to, it's something to think about, right? So anyway, if we're looping over here, then what I need to do inside each of these ones is just figure out whether what the closest tile would be. So the first thing I need to do is I need to look up that tile, right? So I want to say what's the tile value in that area, right? And so I believe we have a way of doing that just flat out, which I do, and so I can pass these guys in there and get what the tile value is. So here's the tile value. I can look at that tile value and say if tile value is empty, right? I believe it's is 1 is our blocking thing. Let me make sure. Yeah. Like that. And for now, I guess maybe since I've got enough of it, I'll also do a thing that is tile value empty. So, right, something like this. Does that make sense? Just so I can reuse that check. Is tile value empty? Tile value, so on. That way I don't have to keep thinking about it. And again, we're going to replace this stuff anyway because we're going to have to decide much later on, probably after we do the render and we start thinking about what's actually in a given game tile, we'll have a representation for the game tile. For right now, we just have some numbers we throw in there for no apparent reason, just so we can have some variety and think about what's actually in the tile, right? But that way we can say empty equals is tile value empty, and then we pass that, and this tells us whether it's empty. So then I'll just do is tile value empty, like so on. And if it is, then we can actually check to see if we can stand anywhere in the tile or see where the closest point in the tile is, and if not, we won't, right? Okay. So the next thing we have to do is check the tiles all around us, right? We need to figure out what our rectangular space looks like for this for the purposes of checking. Now, one thing I got to think about here, because I'm not even sure myself. I got to think about this. Never done this before on a tile map. Tile maps are new to me, by the way. I just decided I kind of wanted to do them for this game because I'd never done a tile map game. So, you know, stuff I got to think about too. So in the tile map, let's say that we've got a guy here, right? What does that imply for our circular, if we had a circular style hero, right? Well, it means that from at least right here, we've got the radius worth where he could stand. And then I guess what it does is it makes it look like this, right? Meaning he can stand anywhere in something that looks like this, right? And that is rounded right there in some sense, right? He could get closer to it. So there's basically like a arc that's his radius wide coming from the corner that cuts out that segment of the thing, right? Because if you imagine the dude standing and he has to stand, you know, I'm talking about this, right? You imagine him coming up, he's a circle or something. He's coming up to this point, and if he's going to run into that point, then basically what's going to happen to him is this radius of the circle, this R, if he came into it this way along this edge, he would stop R away from it. He'd hit it R away from it. And if he came into it this edge, he would stop R away from it as well. And then he could walk all around it, always maintaining R's distance. So essentially you've got that kind of notch in there, right? So basically the shape of the area in which he can stand is, if there's a solid wall here, then it's just R, it's that whatever that radius is moved in. But if there's if there's diagonals, then there's notches like that. Right? Does that make sense? Hopefully that makes some sense. So basically there's like 4 walls that could be there for him, and 4 notches that could be there for him. And we don't really have to handle the notches right now if we don't want to. We could just not handle those cases. Like I said, we just have to spec out that we want the engine to handle them. So maybe we'll skip them for now so that we don't have to spend a lot of time doing that when we're just trying to do spec code. But, you know, we got to know. We got to say that that's what we want to have happen, right? All right, so is tile value map empty there? If it is, then we have to go and say, all right, let's define the actual valid region where the player could actually be inside this tile. And so essentially that's going to be a min max x and a min max y, right? And so we'll make those v2s for now. So let's say we got our min corner and our max corner, and we'll initialize where those are, like where the actual min and max corner are. We know what those are. Those are the tile side in meters. In meters, right? Divided by 2, right? So basically, I know that the min corner is at there, because remember, everything's tile relative. So from the center of the tile, it's half that which is kind of tile x. We don't actually check. He's not upwards. They just walk up, like specific tiles are like ladders that go up or something. That's typically how these games work. So we'll have to see, what we want to do when we actually get to the point where we've got, where we're really thinking about how we want it to look when the player goes up, right? But the abs tile z is just wherever the player was, and the tile side meters is, I believe, what we're going to do here. And we could do just right now that search. We could do the search right now. So the first thing we could do is say, well, and let's walk through this search. We don't have a whole lot of time left, so I don't think we're going to finish this today. We've only got 10 minutes left, so we'll do maybe part of it today, and we'll do part of it start picking up again on Monday. So if we think about how we want to do this search, right? We've come up with a tile, right? We've looked at, and this is the part we're going to do next. We've looked at, let's say, what's blocking him, and we've come up with a rectangle that's where he could stand inside this tile. And now we have a point somewhere, and we want to know what the closest point in our rectangle is to that point. So what are all the cases, right? Well, the cases are either the points inside our rectangle, right? So the point's like somewhere in here, right? If the point's inside, then it's just the point, right? So one case is, it's just the point if it's inside. So if it's inside, it's just the point. If it's not inside, that means that nowhere inside this rectangle could possibly be the closest point. The only places that could be the closest point are on the edges, right? It would have to be on the edges. So if it's on the edges, then what we need to do is we need to check each edge, right? And which edge do we need to check, right? Well, we need to check whichever edge is implied by the delta between the tile center and this guy, right? So when we check and we look where this guy is, all we really need to do is go, well, is it less than or greater than in x for us, right? If it's less than x for us, in fact, you know what? This is going to be such a cakewalk. All we really need to do is say, okay, if it's less than that, this is basically just a trivial clipping problem, right? It's really nothing to it. We just start with this and say, okay, if he's less than our minimum bound, then just put him at the minimum bound, right? And if he's less than our if he's less than our maximum bound, yeah, this is going to be really, really simple. This is going to be really, really simple. So the closest point, right, would be here in this case, I believe, right? Is that correct? So if we're looking at what the closest point is, no, that's not true. The closest point would be here. Yeah. Okay, even better. All right. Sorry, I got distracted there for a second, thinking the problem through. All right, so the closest point to a rectangle is actually just going to always be a perpendicular to the edge, right? Because I was thinking closest point to the center there, and I was like, oh, we got to find the intersection. Not true, because we're not looking for the closest point to the center. We're looking for the closest point to the rectangle. So basically, this coordinate, whatever this coordinate is relative to the center, is the closest point once you actually clip its coordinates to the coordinates we have. So if it's less than our min x, we just clip it to our min x, and bam, it's the closest point, right? If it's less than, if it's greater than the x or the greater than the y, we just clip it to. And as long as we just sort of clip it to whatever it is, then we've got that closest point. I think that's it. And that'll handle the corner cases properly too, because it'll clip it here. Like if it was out here, it'd first clip it to here and then clip it to here. And that's exactly what we would want. So basically all we have to do is just go through each axis, x and then y, clipping it to the bounds in that, and we've got the closest point. Done, right? So to me, that sounds like something that I just want to call here. I want to say closest right point in rectangle. It seems like something we might want to do. Just in general, it's a nice easy thing for me to say. So I'm going to say that our test P is whatever the closest point in the rectangle is. I'm going to pass that rectangle, min corner, max corner, right? So the closest point in the rectangle to that new player P, so relative new player P. And so to produce the relative new player P, I just need to know the difference between that new player P, right? This guy right here. Where's that subtraction? I've got that diff function. That's what I want. So what I want to do here is say, all right, I've got that diff function. I want to subtract these two guys. I want to subtract the tile point. So this is going to be my my test tile, and this is going to be my new player P, like so on. That. And the test tile P I need to build out of the abs tile X, abs tile Y, and we don't actually even have a function for that yet, do we? So our tile map position, I'd like to be able to make one of these easily without having to specify the offset, which I could do just by doing it directly, but I'd like to be able to search for those. So I think what I'm going to do is introduce something here where I can sort of say, you know, centered tile point, or something like that, and I just pass abs tile X, abs tile Y, and abs tile Z, like so on, and can basically produce the result that way. So result is just a straight copy of those things. And it is assumed that just like the other fields are 0. So we'll return that, like that, and that way I can quickly generate this guy, you know, with actually no. And again, we're not thinking about speed here at all. That's important to remember. We're just thinking about writing code that works at this point, and all the stuff that we worry about speed, that's all going to come later on down the road. So I try to be aware of algorithmic problems if there's a speed problem in that sense, but you know, I try not to think about that in terms of when we're just working on the code directly. All right, so let's go ahead and compile that, and now we have to, let's see, what is the problem here? Cannot convert argument 2. Oh, right, these are addresses. Am I correct about that? Yeah. And so this is rel new player P. So now we got that relative one. So all we now have to do is do that. So assuming that we have that, we have our best point. Our best point is going to be wherever we start. So the way that I'm going to treat this is I'm going to say wherever the player is right now, that's going to be the best point, right? So the tile map position that we expect, our best player P, right, is going to be wherever he is right now. That's just what we're going to do. And then so this is what we're moving. Is going to be the length vector. You could just do the square root of the vector with its own inner product, right? But we never actually typed that in. So there's actually, if I just want to get the length squared of a particular vector, maybe I'll call that length SQ. That seems a little bit better. There we go. If you just want to get the length squared, we actually already did the math for that on the previous stream. It's just that, right? And that's, we wouldn't really even have to introduce a function for that. It's just a little easier to read. It's like easier for the person to read. Now, why am I leaving it squared instead of taking the square root to find its length? Well, square roots is extra work we don't actually have to do because we never actually care what the distance is. We just care if the distance is less. And we know that the square of a number that's less than another number is also less than the square of that other number, right? We know that if x is less than y, then x squared is also less than y squared as long as the numbers are both the same sign, right? As long as they're both positive, for example, we know that that's true. If they were negative, they might flip. In this case, it might be different, right? But this is the case for positive, and we know that distances are always positive. Like the length that you go, the length is always going to be positive. There's no way for it to be negative, so we're totally fine, right? So in this case, that's totally sufficient, and all we would do here is actually test to see whether it's better. And of course, I'm out of time, so we'll do that tomorrow. We'll do that on Monday and finish that up. You start with variable names with uppercase, struct names with lower. Is that the standard C way or just how you do it? I'm used to the opposite, which is why I'm asking. It's just how I do it. I think the standard way is actually to have everything be lowercase with underscores, maybe, is more standard. I don't know, but this is just the way that I did it. It actually originally comes from Chris Hecker's style, because I was programming the first job I got when I was first programming in the game industry was with him, and that's the way he usually had his code structured. So I just ended up picking that up. I think before that I did everything was lowercase with underscores. How do you think we would determine using this system if the player should be killed by a collision, like walls closing in and crushing you or whatever? Well, that's a good question. I don't know that I don't know how much I would necessarily say that I want to have stuff where that necessarily happens, but the easiest way to do it is just to go, well, that first move that you make, so I'm here and I try to move here, whatever you were inside at that time could have consequences. So if you're trying to make it so that if you touch a wall that kills you, you'd just do that. So if I would have been inside a spiky killy thing, then that kills me. On the other hand, if I end up in a situation where I cannot stand in my current position and I cannot find a point that's close to me, that would be I cannot find a point I could move to that's within the boundaries of how far the player is allowed to move, then I know that walls have closed in on me. And again, I would do whatever is the place that I'm standing. I would just do whatever is in that location would have its effect, right? So it's actually really really easy to handle both those cases. But like I said, I don't know if we'll have those or not. If we do, that's how we would handle them. Abner wants to know if I ever fall for some of the dogmatic traps anymore when I'm coding. I don't know. That's a good question. Not very often. I don't think so. But I do write lousy code still, right? Like, I don't think I fall for the dogmatic traps. But the bottom line is that, like, I'll still sometimes write code that isn't very good, right? That's algorithmically not very good. And you're just like, yep, this was not very good. And that's because you can, it's easy to eventually train yourself to avoid problems with your coding style that are causing you to do like more work than you should have done or to do things poorly. But the bottom line is there's just a lot of work that goes into writing something correctly, and sometimes you just don't do that work. And it has nothing to do with like what the code looks like. It's that it's actually just structure. The actual algorithm is not very good, right? And I definitely do that on projects, you know, like Fabian recently had to deal with one of my code generators, which was super janky. And like, you know, I was like, it only did exactly what it needed to do for what I had in mind for it. And like, of course, he was doing some stuff on Bink 2 afterwards and had to deal with it. And I do not relish being in his position, right? Because I definitely did not set him up for success. So he had to do a bunch of work to it to fix a bunch of things that were bad in it. But I don't, like, most of those were not because I had some dogmatic coding style that I felt. It was just because the code was lousy, right? And the algorithms were lousy because I just did the simplest thing that needed to get done, instead of going, hey, I should take some time here to think about this is something that people are going to have to use later. Let's go ahead and actually do more work on it. And so sometimes, you know, that's something that I still do, which is I don't go and take the time to go, okay, hold on. Now that we've got things doing what I need it to do, let's push a little further. If I know that this is something that's going to stick around, let's push a little further and actually go do the cleanup and the extension that you should do if you were going to actually prepare the next person for success. So I definitely have that problem still. So, you know, there's that. So does the search method here give us a sense of rounded corners? Yes. Well, the search... I don't really understand the searching stuff. Why not just adjust the player's vector based on normal vectors? So I thought I kind of explained that in terms of what had to happen, but maybe I didn't. So let's say I'm here, and this is my velocity vector, right? So if I don't do search in P, if I do search in T, which is the standard, first I have to write collision code that checks the collision of these two things, right? So I have to generate something that'll produce this point, at least. That's the first thing. And rather, it has to actually produce the correct point for the circular collision. So it actually has to produce this point, right? Then I have to update based on the normal, which at that point would be here, right? So now here's my new velocity vector. I then have to rerun this and find, oh, he can't step to here either. He would actually only step to here, right? And then I have to correct the velocity vector again, right? And then if I still had some left, I might find that he couldn't step to here either. He would actually step to here, and here, and here. And I would end up doing 1, 2, 3, 4, 5, 6 steps of that thing. And they're all super numerically fiddly, right? Like I have to make sure that numerically I did this correctly because, oh, I'm adjusting these vectors and doing all this stuff in this sort of weird crenellation space. And again, this has the problem of if I had a little sort of chink in the wall, a little like thing that kind of opens up there, it wouldn't handle that. I would just stop dead right there. There'd be no way to fix that because when I deaden the velocity, when I use only the remaining part of the velocity, he'd just stop right in that corner. So search in T is lousy in my opinion. Search in P is just way better because it doesn't have any of these problems. So it's So there's that. I'm not sure if that's what you were asking, but. Are you going to worry about how many objects collisions the collision detection system can handle? For search in P, don't you have a problem with passing through walls thinner than the player's movement vector? No. So the reason you don't is because that flood fill, like I said. So you always start with, when you're doing your cell search, right? And this is true in Handmade, this will be true in Handmade Hero as well. So even though we maybe never have the case in Handmade Hero, it's true in Handmade Hero as well. If you want to do this, the search has to flood fill out and reach the wall, and reach the target location. And so assuming that there's a wall like this and you're trying to pass through it, you know, he's only allowed to basically go a certain distance in the flood fill. So he can't actually ever get over to here because he'd never actually reach those cells. If that's why I was talking about that flood fill before, because it prevents you from ever considering this at all. You could do something really weird where you allowed the player to teleport through walls if he could ever get there, which would allow him to search much farther away, which I don't think you actually want to do, but it's interesting because it would enable an interesting Will the characters have skeletal or old school sprite animations? Skeletal. Just because it's more work, and you know, for educational purposes, it'll show more stuff. Let's see. That's it. Garlando Bloom, that sounds like a good idea since the game needs secrets. Yeah, I think it is possibly. I mean, I don't know. Like I said, I don't really know. Yesterday, we just took a little bit of time to fix, well, a bug, but basically in fixing that bug, we decided to kind of add a feature, which is multiple people controlling multiple entities on the screen. And so we basically had the ability for people to kind of drop in, if I got a gamepad here, I can add another guy, right? And he's there hanging out. Now, we started basically pulling out the code for the sprite control for that hero character into its own function, and he's kind of doing his thing, right? But what we had interrupted to do that yesterday, because I wanted to take care of that right away, what we interrupted is we interrupted fixing our wall sticking problem, which we had discussed and we were in the process of writing code for. Now, I want to talk about that a little bit, but one thing I did want to do too is while we're at it, at the beginning of the stream here, I want to clean up one more thing because now that we actually have now that we actually have multiple little heroes on here, we're supporting the analog stick now. I want to go in there and deal with some stuff that we didn't deal with on the analog stick in terms of the motion of the actual player. So, just quickly. If you recall, we had not really learned vectors yet when we first visited. Let's see here. When we first visited this code right here. So what we were doing originally is we basically just did a little hack which said that if both of your when the user is controlling the hero, we had just hacked in a thing so that when he tries to move diagonally, he wouldn't move faster than he moved when he was moving in cardinal directions, right? And this is something that we did before we learned vectors. So basically, we had a situation where we had something that looks like this. We have him moving in this direction, and we would set this to be 1y and 0x. So this was the vector 0, 1, right? Or we would be moving this way, and this would be the vector 1, 0. Or we would be moving this way. Oh, sorry, that's actually negative 1. And that's 0, 1, because remember, y goes up. That's positive x, positive y. And this is negative 1, right? These are the vectors that the D-pad could be creating by pushing in the cardinal directions. But when you push in two directions at once, we were ending up the vector like 1, 1. Right? Which is longer, if you remember, by root 2. We went through all this, so jump back to videos if you're not sure what I'm talking about. I'm not going to go over it all again today. But we would basically end up with this, and that's moving faster than either of these. It's root 2 long instead of 1 long, right? And so what we decided to do is we decided to solve, we actually solved Pythagorean theorem to figure out how long it should be so that it would be the same length. It would still be 1 long, but just in that direction, right? But now we have a different problem. If the analog stick is being used, then really inside this unit circle, right, you could imagine the analog stick pushing in any direction, and it can be pushing proportionally. So it doesn't have to be just one of these cardinal directions or the diagonal, right? So all we really want to do is we want to make sure that that vector that comes back from the analog stick, we just want to use that as his acceleration directly, unless for some reason the value we get back tries to exceed the length of 1, right? Tries to exceed the length of 1 so that it would be accelerating beyond the maximum acceleration that we wanted it to have, right? And while we don't necessarily know if that will ever happen, because it could be that the analog stick always returns values that are perfectly inside that unit circle, you could imagine if there was some gamepad that had more of a square range of motion so that when you pushed it up into the corner here, it was actually kind of more at negative acceleration vector that we would get this, right? Ax squared, the length squared of this square root. I just want someone to give us a little graph, and I figured it'd be easier. One. It's right, that's the one value where the square root of the number equals itself. It's the identity for square root, right? So if I take the square root of 1, I actually get 1 back. So I need to construct a kind of diagram that, again, should be familiar to you from your high school math, right? So let's say I want to do it a little more sort of aggressively. Pretty straightforward. Now, as I said before, if you want to know why we are making it length 1, it's because basically anything that's length 1 is easy to then transform out into some other length, right? Because if I know something is already length 1 and I want to make it some other length later, I just multiply it by the length that I want, right? Because you have to remember this equation that I just said, where it's the new length, right, over the old length. If I wanted to make something a new length and I already knew its old length was 1, well, that means this square root here would just already be 1. And so it would just be new length over 1 or new length. So that would be the equation, right, for changing it to some new length if I knew its current length was already 1. And so the reason I'm constructing a length 1 vector here is because now I just have basically the generic vector that points in the direction that the person goes, or a vector that's something less than 1. And if it's something less than 1, then all it will do is when I multiply it by something later, it will be proportionally less, which is exactly what I would want with the analog stick, right? I'd want a proportion less than whatever I'm going to do if it was pushed all the way out. And so then we do exactly what I just said. we take that vector and we multiply it by however fast we wanted the player to actually accelerate in meters per second squared. And that basically gives us a vector that's the correct length now for acceleration to use. And then we proceed as normal. So nothing weird happens there. So that's it. I mean, there's nothing really fancy going on there. I just want to make sure everyone kind of understood what was going on. And so then, hey, there he goes, and he's good. So now all we have to do is concentrate on this problem, right? Where we're not grinding along the wall because we don't allow movement when we detect a collision, right? And so what we want to do is allow movement when we detect a collision now and clean that up. Okay. So what we need to do for that, I thought about this quite a bit, and I talked about, on a previous stream, I was talking about whether we should do search in P or search in T, and I kind of talked about how to implement both methods, and the more I think about it, the less I want to do search in P. I was kind of like really on the fence, if you remember. I wasn't sure, and I thought about it over the weekend, and I was like, you know what, I don't think it's a good idea. And the reason I don't think it's a good idea is because I feel like it's going to introduce a lot of complexity into the code for us for not a lot of benefit. Because really in this game, we're not going to be grinding against walls a lot. It's not like a walking simulator kind of a game. And I feel like the benefit that we'd get from having search in P, which I like better for collision detection in some case sense, is just going to cost too much in terms of the code complexity. So I think since we really never actually bothered to implement it, I'm just going to say let's not bother, and let's go with the more traditional version, which I was going to show how to implement anyway. Let's just do that method, because I think that method makes more sense because it's cheaper is the thing. And I feel like the cheapness is going to be important for us, that's all. And I don't think we're going to get much benefit out of the other way. So basically all we really needed to do was come up with a better way of actually detecting when we were hitting stuff. So all we were doing before is when we actually go in, somewhere, we say we're here and over a time step we want to go here, but there's something in our way. All we were doing before is checking that ending location. We were checking that ending location to see whether we could stand there. And if we could, we just accepted the move. If we couldn't, we denied the move. That was it. And so we need to do something better than that. And in order to do something better than that, the first thing we have to do is figure out what we actually hit and where we hit it. So we need to do something where we're going to look at what we could collide with. And we have to go ahead and say, all right, when we collide with something, let's figure out where we collided. And when we figure out where we collided, we will put the player there, right? We will update his velocity vector, which is what we were doing before, to basically not have any of the component that was going into the thing that he collided against. And then we will try again to move him. Now, we will try a few times. We will basically do this in a loop that tries a few times to get him to where he should be. And if it fails to get him to where he should be, I shouldn't say where he should be. It'll try a few times to move him the total amount that it should have moved him, right? Because when we go here, we'll find the velocity vector still there's still a delta t, right? Because we moved to here, and we know that he would have gotten there if this was the entire time step. We know that we would have gotten to here in less than that. So there's some smaller thing here, delta t 2 or something, right? That's a smaller thing. And we want to then use the remainder, that delta t remainder, we want to still try to move him by that much. And so hopefully delta t, the amount that's remaining, goes down to 0, and we know that we've done a complete move. But if we find that we just can't resolve it because there's all these crazy walls in there and he's bouncing around or whatever, we'll just cut our losses and say, after 4 iterations or something, we're just going to consider that good enough and we'll stop. Because we don't want to have something where we're going to do an unbounded number of iterations. That's just a very bad idea. For something that's performance-oriented. And again, this whole thing is very tiny. We're talking about something that happens over a 30th or a 60th of a second. So these are like microscopic movements that we're talking about here. So how many bounces we support is not particularly relevant in terms of what the player can actually experience. As long as it's like 2 or 3, I think we should be fine. So what I need to do is figure out how to compute that, right? I need to figure out how to compute that, and we'll start by computing it for the simplest case that we possibly could. We'll start by computing it with point versus line, essentially, right? So what we want to do is say, all right, we need to, we're going to have some kind of line, right? And we're going to have some representation for our guy and some concept of the direction he's going. And we need to figure out when he hits that sort of whatever that is, that line, that blocker. So we're going to start with that as the simplest case, and we'll kind of work up from there, because I think, I don't know how much time we got left. So we got about a half hour left. So that'll be quite a bit for us to actually go through in such a short amount of time, actually. So let's focus on doing that, and then we will go ahead and see when we get done with that. We'll probably maybe tomorrow talk about how to do some more complicated stuff. Okay, so if we're just doing that simple case, what we need to start thinking about is how to solve equations with these vectors, right? Because typically when you have something like this, if I have something like that where I've got some kind of a line segment, right, like so, and I have some kind of a vector that's going in that direction, I now need to figure out how to do solves, because in order to figure out when, if I was going along this line, when I go here, we're essentially talking about something that's going to be some function of time, right? As time progresses, I'm moving. And I want to know when this function of time that tells me like a location of the player, when it equals some particular criteria, right? I've got some value that I want to satisfy here, and I need to know when that becomes equal to something, right? And so if I want to do that, we're starting to talk about actually solving some equations. And so the first question is, well, what is the equations? What is the first equation what is the first part of the equation that we're going to use? How do we represent this part? How do we represent there's a player and he's at a location and he's moving, right? Well, the most simple thing to do here, right, is to say, well, I start at a place, we'll call that P0, right? And then I move along some vector that's like a distance, right? I move in a direction. So I know that I've got some, P0, which is this point here, and then I know I've got some direction, we'll call that D, and I'm moving along it in, some amount. So if you remember, we did that thing where we talked about the linear blend, right? And we said, oh, well, if you want to have a linear blend between 2 points, A and B, right, you can think of it as the delta between them, right, B minus A. You can think of that delta between them, you can think of starting at A and adding some percentage of that distance between them, right? And this was the standard linear blend function, and I said it comes up all the time, right? Remember I said everything we do is going to have this in it. Well, guess what? It's going to happen here too. I've got a place I'm going to, I've got a place I'm coming from, right? And I want to move between them. Classic linear blend, right? So I'm going to talk about this as if I have this vector. So we're going to say that I have that delta vector there, right? And like I said, I'm going to call that D. So I'm going to call this difference between D. And so I'm just talking about that P0, which is this. I'm talking about P0 plus T times D, right? That will tell me where my guy is at any time T, right? So if he starts from here, I can plug in any time I want, and he will move along that line and just keep going, right? Now, if I want to, I can do different things here. I can phrase this in a couple different ways. I can say that D is the full distance that he moves. So it's like B minus A, if in this case here, or like this is the P1 he's going to. So in this case, it would be P1 minus P0. I could say that. And what that would mean is that T is normalized. It means that T ranges from 0 to 1, right? And when he gets to 1, he's done moving for this. That's as far as he can go, right? I could, on the other hand, also take D and say that D has length 1. The length of D is 1, right? That would be normalizing the D vector. And then T would range from 0 to whatever the actual amount is that would get him along that vector to the location, right? It would be his motion amount. So we have different ways we could phrase this. We could have T range from 0 to some value, or we can have it range from 0 to 1. And it depends on what we want our properties to be of these vectors. Do we want this to be normalized? Do we care? Stuff like that. So just keeping in mind that this could actually be phrased a couple different ways. The P0 is kind of unambiguous. It's where we started at the beginning of time step, where the player is standing right now. The D is somewhat ambiguous in that we know it's pointing in the direction of motion. But in terms of the T and the length of D, they are kind of interchangeable. We can move between different schemes there depending on how we want it to work, right? Okay, so let's start with the simplest possible case we could imagine, right? The simplest possible case would be if we just know that we have, like, say, a vertical wall, right? We just want to know when this guy hits a vertical wall that extends, let's say, infinitely for now. So this is just an infinite vertical wall. He cannot go past it, ever. He'll never get past that wall, whether he goes up, down, any other way. Well, what do we know about a vertical wall? We know a vertical wall has an x-coordinate of something and a y-coordinate of everything, right? Any y-coordinate that you want is on that wall, but it only has one x-coordinate, right? So this can be anything, but this would have to be a specific value. And that would basically be like our wall x, right, or something. So we'll call that wall x. So if we want to, we could now imagine how we would directly solve this equation to see when a guy walking in that direction, right, would hit this wall. We would say we want to know when the x component of this, so ptx, which is p0x plus t dx, remember, because this is a vector equation, and I can always look at its scalar parts by just looking at the particular x component of it. If I have this equation, all I need to do is say whenever that equals the wall x, right? So this right here is the equation I would solve to tell me when I would hit that in t. So if I want to actually solve it, right, I can just solve for t. I get t dx equals wx minus p0x, right? I subtract this over to this side, so that goes over here. And then I divide by dx to get rid of the dx, right? So get rid of that and put it under here. Divide by dx, okay? So this is the time at which I would hit that wall. Simple enough, right? Not particularly complicated. But there's a catch here. I now have well, you know what? I should probably be slyer about that. Does anyone know what the catch is here? Maybe you guys already know. There's a catch here, and I haven't mentioned it yet. We'll kind of see if anyone will give you a chance to think about it a little bit. But I want to point it out. I wish I had more tea, but I'm regretfully out of tea. All right, so the catch is right here. When you divide by dx, you may remember from your high school math classes, someone would always say, you know, the teacher would always say, subject to dx not equal to 0, right? They would say, I'm going to write it in our form, not math form, right? dx can't be 0. I guess the math form is more typically that way, right? And they say that because dx can't be 0 because dividing by 0 is undefined behavior in math. You don't know what it is. At least it's undefined behavior in some math. The math we're doing, it's undefined. And since that's the case, since you can't divide by 0, you know that your solution to this equation depends on dx having been set to some value that isn't 0. Now, you may have always wondered, I don't care about that. What is that for? It's just lame, stupid. I don't care. When you were in a high school math class, it's just annoying, right? But it's not annoying when you actually get to start using math for real. You realize it's very important and it's interesting. What does that mean? Well, what it means is, think about this vector. This is the vector d. What are its components? It is dx dy, right? That's the components. We're talking about this, the x-coordinate of the vector. That's how far it is like this. So, you know, if I have my vector here, you know, here's my vector d. We're talking about dx. It's down here, and here's dy. Well, if dx was 0, that means that the vector is pointing in either up or down, straight up or down. It's not pointing to left or right at all, right? Or it's not pointing anywhere. It's just 0. But if that were true, if this is pointing straight up or straight down, well, guess what? It's parallel to this line. So there is no solution to when he will hit this line, when the person walking along that will hit it. There's no solution because he'll never hit it. He can walk as long as he wants. He can walk to the end of time and he'll never hit that wall, right? So what was stupid in math class, rightfully so, is actually quite nice in game programming. It is information, and that information has real meaning. And that's one of the most satisfying things about math, is when you actually start to use it, you realize that all the stupid crap actually means stuff, and you use it, right? So when we're going to implement this, we have to look and say, oh, okay, if the x coordinate is very close to 0, this is becoming an undefined equation. We just assume that he can't hit the wall at that point, right? And we don't have to check against this wall at all because he'll never hit it. So what's the rest of this mean? This t-value that comes back, assuming that he can't hit the wall, so it's got some x component. Well, the t-value is either going to be positive, which means he goes some direction and hits it, or it's going to be negative, which means that like he was actually walking in the opposite direction of the wall, and he would have hit it if he'd walked backwards some amount of time. So this solution actually gives us how far it would take him to reach the wall walking forwards or backwards, and it tells us which one of them it would have been, right? So that's kind of cool. But we can, when this comes back, we can go, oh, we're just going to say we only care about stuff that's t greater than or equal to 0, because we actually don't care about him walking backwards into the wall. We're only checking the forwards, right? So that would be a pretty simple thing for us to test and to see what happens when he walks into vertical or, of course, horizontal walls would be the same. We just change this to wx, the wx and the px and dx would all change to y, right? So we now have that sort of, oh, you know what? I'm gonna try it. You guys ready for this? I'm gonna try it. Scrolling over. Check it out. Man, that's cool. All right. So this is the equation. The t equals wx minus p0x over dx, right? That's the equation that we would use to solve for an x wall. And similarly, if we wanted to solve for a y wall, right? We would say the same thing, but in y, right? So that's how we solve for vertical or horizontal walls. Now with that, we can actually go implement mostly our tile map collision. And maybe we should do that. Maybe that is what we'll do. And then tomorrow we'll talk about how to do more arbitrary stuff. So if you think about this, when you think about this, we go, okay, when we do these collision detections, right? Excuse me. We would be colliding against infinite walls. So we have stuff in our game where we've got these walls that have like holes in them and stuff. That wouldn't work, right? Because if we started colliding against this wall here, where, you know, here's the walls, right? And the hero's trying to go through this door, he'd never be able to get through there because the wall is infinitely high, right? It's just, it goes up and down and covers everything because it's an infinitely long wall. It's just testing against one thing. But obviously, if we wanted to, we could fix that pretty easily, right? Because when we find out where this would actually be, like when we find out what the actual collision time is, right? We could then say, well, use that t-value, because we have this function here, right? Plug that t-value back into the walking equation, find out where the guy is standing at that time, right? So do p0 plus, and let's call this like our solved for t or something, plus t solve, right, times d. This right here will give us the solved for time p. That will give us this, when he walks, that'll give us this location when he hits the wall, right? When he hits the wall, we can check the y coordinate to see what its range is. And if that range is not in between the two locations that we know of the wall to be, right, we could just not do it. So for every for every tile block that's solid, we could basically check 4 different collisions, right? One for each side of the block, and just check the range of the collision to make sure it's actually in between there. If it's not, we don't count it as a collision. We just move on. And so that's a pretty easy way, right, that we could do this. So let's go ahead and implement that. Since this may be very new to a lot of people, I figure like we shouldn't really jump ahead at all, if that makes sense. So that makes sense. Hopefully that makes sense. And so that's actually another discussion we kind of have to have. Well, there's a lot involved here. I got to explain a lot of stuff. This may be very new to a lot of people. I figure like what we need to do is solid. So the first thing we need to figure out is which tiles do we actually want to check, right? Like what are the tiles that actually need to be checked? And so that's actually another discussion we kind of have to have. Well, there's a lot involved here. I got to explain a lot of stuff. We may not get through all of this tonight. All right. So if you imagine what's happening here, collision detection is complicated. Why can't I? Oh, I'm just because I got some stuff selected. So many things I have to do prerequisite-wise. All right. So if you imagine that I have my tile map, then we have to ask the question, what are the things that I actually have to collide with? If like my guy is, say, here, and the time step would move him to here, right? Well, the answer is I need to check all of the tiles that he could have gone through. So I need to check like the tile that I'm standing on. I need to check the tile that he would end up in and all the tiles in between, right? And so if you think about what that means, it's basically just a min-max situation, right? It's the minimum tile y and the maximum tile y and the minimum tile x and the maximum tile x of the two locations, where he is and where he's going. Because if he was going to go like that or something like this, we'd want to check this whole rectangle, right? Because we want to check all of these things for collision. Now, really, if we wanted to be, that's a conservative check, right? A conservative check means it checks perhaps more than enough things, right? A conservative check is basically one that doesn't necessarily check the fewest number of things, but it definitely checks all the things it has to, right? We could do better in the cases where we had something like this by actually saying, well, okay, the line the player moved doesn't actually pass through these guys here, right? It only passes through this one, this one, this one, and this one. So we don't have to do the full rectangle, right? And that's definitely something to think about when we're actually implementing the engine for reals, because that could save time. But again, these aren't going to be there's really no way to pass through that many tiles unless you're moving extremely quickly. But yeah, just something to think about. So all we really need to do is a conservative check at this point, which will basically say, okay, as long as we get all the tiles we might check, we'll be fine. It doesn't matter if we check some ones that we actually shouldn't have checked, because that's just like some wasted time, and that's like stuff to worry about in the optimization phase of things. So we don't actually care about that for now. So what we want to do is basically say, okay, the two places, place we're coming from, the place we're going to, we want to take the min and max tile values of those and to know which tiles to check. So the min tile x is just going to be the minimum. I don't know if we never actually did we actually ever do minimum and maximum macros? I don't know if we did. Handmade platform.h, did we do a min and max? Basically, if we want to do a minimum or a maximum of two things, so I've got two values, whatever they are, it's pretty easy to do that check, right? We can just say, if A is less than B, then the thing you wanted was A, right? And if not, then the thing you wanted was B. Pretty simple, right? And the same is true for the maximum. If A was greater than B, right, then you'd want A, otherwise you'd want B. That's pretty much all I'm talking about here. Very, very straightforward, really nothing to it. But what I would like to do now is say, okay, so I've got the old player P and I've got the new player P. So let's take whatever his abs tile, whichever one of those is a greater, is a smaller for that one and greater absolute tile index. Oops, there we go. And then what I have to do is I have to add one, because I want one past the maximum tile. And again, the reason I'm doing that is to make sure that wrapping works properly, if that makes sense. So there we go, max tile. Let's get that Y in there. And then this one will be minimum. There we go. So basically, I just got to get that minimum tile. I got to get that maximum tile. And then I'm going to loop and add one to it, so I'm one past it. And then I loop over those tiles, making sure that I stop when I get to that maximum one. Right? And again, I had to use not equals, not less than, because I want to support wrapping. And you can't support wrapping with a less than, because if I underflow here and the min tile was less, then that would be no good. All right. So what I need to do now is say, okay, how can sometimes players enter glitchingly through the corners of walls or fall through them? Is that an art mistake or programming? The answer is it can actually be either. So basically, you can have two conditions happen there. One is that the collision geometry is just wrong, right? And so one case is I've got a thing and it looks like that, right? The collision geometry looks like this, and the player is only that big and he fits between them. And then he can glitch through it. So even though maybe it's drawn like a solid thing, the collision geometry is wrong and he can glitch through it. Another one's a programming bug. The programming bug happens when the collision resolve is not robust in the face of tweaky situations, right? So let's say like I'm jamming into a corner here, and that corner basically has, a couple different things abutting in it like this. you know, something like that. And maybe this is empty here and this is empty here. And so these two things kind of abut. And I've got this thing where I can glitch through there because I'm not conservative about how I'm checking for the collision with my guy somehow, right? That could certainly occur. It occurs in cases. Without further ado, let's get back to where we were yesterday, which was very deflating because I was just about to finish some code and we had to end the stream because the stream was over. So let's take a look at what was going on there. If you remember, we had our little dude here, right? And we were about to do some collision work with him. And we wanted to be able to have him run into the walls properly. You can see he sticks on the walls right now. And so what we need to do is we need to fix that. We wanted to make a good collision thing so that we'd be kind of all set to go. All right, so how do we do that? Well, we started writing something. I was sort of teaching collision detection in baby steps. And so we were going down each individual baby step, and we got to the baby step of how to test against just simple walls. So just a point, like a moving point versus one horizontal or vertical wall. And we wrote the equations. When we do this computation for t result, right, we are going to get the intersection of essentially the whole line that the player is traveling along with that wall, which means he could go backwards and hit the wall, which we don't care about. So what we want to do is also say, well, so let me double check and make sure that that's not the case. What I'm going to do right here is just check to make sure that I don't have a thing where I'm just stepping through the wall because we're not actually doing anything to prevent that at the moment. Yeah, so that's what I thought. All right, so that's fine. So let's talk about that. All right. So we've gotten to the place where we're successfully testing all the walls, but now we have to deal with problem number 2 for this kind of test, which is that when we actually do this computation, right? So here's the problem that we have. When we actually do this, we are finding the point where he exactly hits the wall, where this guy exactly hits the wall, right? And we have a problem, which is that when if we then allow him to actually be there, on the next time step, he won't actually necessarily, you know, due to precision issues and so on, he won't necessarily ever hit this wall because he might be just a little bit to the other side of it, right? Because we're counting on that equation producing a t that is greater than or equal to 0, right? But if we move him right up to the wall and stick him right on it, if we stick him even the smallest fraction of a floating point value to the other side of it, right, then he would not actually, that test would no longer succeed. So we don't have a very big margin for error there, and that's not a good thing, right? That's not a good thing at all, because that's just not how you want to roll, right? So there's a number of ways that we could deal with this. How did he get in there? I'm assuming that that is us not checking something the way that we should be checking, right? Because he shouldn't ever be able to move in like that, right? Like you can see, he can get through there, right? So how did he manage to do that? How did he sneak through that hole? I would like to know. So yeah, you can see that. All right, so I think basically probably the easiest thing to do would just be to step up to the next level of collision detection rather than trying to get this to work more seamlessly, because most of the things that we're seeing here that are janky are things that will go away if we move to the next sort of level of goodness, if that makes sense. So let's just call that done for now, but observe the problems, right? The problems are we have to have an epsilon in order to not go through the wall. And even with that epsilon, I believe, and I can't say for sure because you know what we could do? We could actually do something to visualize this to make it a little easier to see what I think is happening there. And I just want to make sure everyone can see all the problems with it before we go up to the next thing. Let's see here. I want to render these guys a little smaller than they would otherwise be. So like that, I think. So there we go. So did you see that? Basically what happened there? That is exactly what I'm talking about. So I can't get through here, but if I could hit it directly at the edge, right? Where is it? Come on, there we go. Right, did you see that? If I hit it directly at the edge, I can get in between where I was hitting this wall and this wall, right? These two neighboring walls, the two vertical walls, I can just manage to get between it, right? And I think someone on the stream the other day was asking about how you can glitch through walls, and I sort of drew that case where the things were just a little bit off. So that's an example, right? Because numerically, it's just not stable enough. So there's a gap, essentially, that you can sort of fit through there if you kind of work at it, right? So that's a good example. So, all right. So we've got a bunch of things that we would like to do now. And basically, what they boil down to, there's really two totally separate things that we want that both come from the same, that will both be solved by the same solution, if that makes sense. So what are they? All right. Oops, that's no good. Okay. So the first thing is that we are testing against an infinitely thin wall, right? We're testing against something that's like this little tiny thin wall, and all we know about is that pinpoint in space that the wall is. And what that means is that if the guy is on this side of the wall, he can hit it going this way. And if the guy's on this side of the wall, he can hit it going that way. But if he's right here or right here, right? Remember, imagine this was very, very microscopic. So he's just a hair on either side, right? He would still be able to move freely in that direction or freely in that direction, right? So if we're ever off by even the slightest bit numerically, and we thought we were stopping him right here, but we actually put him just on the other side, right? It'll allow the player to tunnel right through the wall. And that's a symptom of the fact that we're treating it as just this thin, right, this very infinitely thin wall. You know what I'm saying? So that's not very good. We don't like that. What we would rather be the case is we'd rather it be the case that this were a solid thing, right? Something that didn't have a very tiny little minuscule sort of thing to it where numerical imprecision could ever happen. We would want this to be as thick, some thickness that allowed it to not get through. And of course, if we think about it, the tile itself, right, is very much a solid thing. So like the fact that we were testing against each wall individually and treating it as infinitely thin isn't really necessary, because the thing that we're trying to simulate is not even an infinitely thin border around something, right? We're actually okay with just saying, hey, you can't walk anywhere within this entire block, right? So what we'd like to do is solve this problem, first of all. But then we have another problem that we also have, right? And that problem is that our guy is too tiny in his collision sense right now, right? He can interpenetrate here because we're only doing collision detection with that point, right? And the reason that we're only doing collision detection with the point is because all we know how to do at this point is do collision detection along a ray, right? So we have a ray that he's moving along, and we're testing that against the wall, but really he should be some shape here, He should be like a circle or something, so that when he moves when he's collision detecting against other things, it's actually whenever any part of the circle would touch the thing that he's colliding against that we'd stop him. And that would allow us to give him some volume, right? So that he stops away from the wall like, there properly, but also if he's going in the other direction, stops away from the wall, like there or whatever, right? So something that gives him that volume back. And I think that's obviously something that we want as well. And so both of those things are basically sort of asking us to move up a level in complexity of how we're doing our collision detection and say, instead of talking just about lines, right? Because all we were talking about is lines. Basically what we wrote before was something that intersects the line of the player, right, with the line of the world, some kind of line in the world. So what we're talking about now is we're saying, let's move from lines to testing actual areas, right? Or volumes if they were in 3D, right? So let's go from lines to areas and figure out how to do area versus area so that we can actually have collision detection that is both numerically more robust because it's not talking about these infinitely thin things that are very easy to have epsilon issues around, A. And B, so that we can make the player have some volume as well, and so he will not be just a pinpoint that's moving around for the purposes of his collision detection. And so that's what we want to do. And ideally, we'd like to do that in a way that gives us a fair bit of flexibility with what these volumes actually are. I would like to basically say maybe at the very least, I'd probably say we might want to allow ellipses in there, right? Because I feel like the guy probably wants to be an ellipse. I don't know. Maybe he wants to be a circle. I don't know. It's kind of hard to say. It depends on what's going to feel good to move around, really, right? But I don't know if a circle makes some sense for him or if an ellipse makes more sense. The problem is, the perspective of the game is a little tilted in that sense. And so maybe it needs to be more of an ellipse to properly feel right in terms of when you're moving through stuff. But at the same time, that means that your motion is going to feel different depending on whether you're grinding against a vertical or a horizontal wall when you turn the edge and stuff. So I don't know, maybe it's a circle. So at the very least, a circle. At the very least, we need circles. Because he's at least going to be probably a circle, because you want him to kind of be smooth and to be able to roll around things so that when you're pushing into things, you don't want him to have you don't want his collision shape to have hard edges because they'll get caught in stuff and be kind of janky to move around. So a circle is kind of nice because it rolls off things and it just feels nice and smooth to move around. So we definitely want circles. And then we probably also want rectangles because there's probably going to be rectangle stuff in the game. But we might also want polygons. Right? We might want to be able to say, let's be able to draw just arbitrary kind of little fancy sorts of things, perhaps, right? So that's another thing that we might want to have. And so we're going to want to basically think about when we upgrade our collision here now, we're going to want to think about how we can do something more along these lines. So what we might do is just do circle and square so that we can do tile map. We could even just do circles and circles. Let's do circle and square. Let's shoot for doing circle and square now. But to think about also polygons going forwards, because when we actually go to do the real shipping collision detector code, whenever we decide to do that, it'd be nice to potentially have those. I'm not sure. I'm not sure if we'll want them, but we might. So we want to basically set our engine up, since that's, we're still in the phase where we want to define all the things we need to do and get, placeholder versions of all of them. I think that's basically what we're looking at. We're looking at circles, squares, and these. And maybe, I don't know if we want rounded rectangles as well. I don't know. We might, rounded, things that are kind of rounded as well. I'm not sure. We will see. But circles and squares will probably be our target for now. So we'll try to do a circles and squares one, and then we'll go from there. I think that pretty much brings us to the end of the stream. It's a short stream a little bit today because we were chatting a little too much at the beginning. Everyone was gabbing. If we change the resolution on Win3Do Handmade, will the tiles in the bitmap still draw the same but smaller, bigger versions of them with the same settings? So right now, we don't have any bitmap scaling code, so the bitmaps always draw pixel to pixel. So if you change the resolution, they'll change size. And that is one good reason, for example, why we would want or potentially at least, want our renderer to be able to handle things like that, at least in the final stages, where it could blow the bitmap out to a bigger size so it always, so it's not dependent on the resolution and so on. Oh, and what about the tiles? Will they still draw the same across the screen with a different resolution? For example, we have 9 by 17 tiles across, and if we switch the resolution, that would be 17 by 9 tile-based. Will we have any bugs and how to fix that? So I'm not sure exactly what you're asking, but basically the idea is the game screen will always be the same. And so right now we don't have the ability to... Okay. We'll talk about two things. So first of all, we're a bitmapped game. So we probably want to run in our native resolution most of the time. So we probably want to run in 1920 by 1080 all the time, right? That's probably what we will do. And so what we'll probably do is we'll draw in 1920 by 1080. And we might also support downscaling by 2. So we might also support running in a half mode where we're running half of that, and where we actually have our bitmaps pre-processed so that they're all half size. And that would be to support like Raspberry Pi and stuff if it's too slow. Or actually more to the point for the Raspberry Pi, too little memory potentially as well. So basically what we will do is we will have a 1920 by 1080 buffer where our tiles are lined up the way that we want them, right? We will draw to it, and then no matter what the ending resolution is, we will blit that up to that resolution, right? Because we don't want to resize every individual thing, because that just wastes a lot of time and will look worse than if we just actually do the whole composite and then scale it up at the end, or down, depending on the circumstance, right?